Before we begin with discussing fractal architecture, let's discuss the goal of software and software design in general. Software has no merit on its own. Software exists to serve some kind of a business purpose. If humans don't benefit from it, it has no use. It's an academic exercise, nothing practical. Now, we know that businesses constantly change. Why? Because the world is dynamic, the world is not static. And businesses must respond to those changes or they die. And the faster the businesses respond to those changes, the better. No business ever said, oh, I wish it would take us longer to respond to this change. Now, because the business software serves the business software has to change too, or itself die. We also know that the system must mimic reality as much as possible. And this has two reasons. One is it's easier for people that understand the business to also understand the software. The software mimics the business. But also, it's better than the alternative. You don't want the business conforming itself to meet a crooked software. And we also know that the software should have the simplest possible design with the fewest possible components. You're in the business of doing less work, not more work. It also stands to reason that if the business wants to do a simple change, it should trigger a simple software change. In general, you could say that it should be easy to design small. Why? Most businesses are not very complex and not very complicated. And if you have a good design with a smaller set of components that you can put together to satisfy any requirements, past and present, future, known and unknown, then you look for the smaller set of components that you can put together to satisfy all of these requirements. And so we're looking for a small set of components that have relatively simple interactions. We also know that the size of the system should be proportional to the size and complexity of the business, and that simple enough businesses should have simple enough software solutions. That, however, is not reality. The reality is that most present-day businesses and the business software are way too complex. And this is true from the smallest to the largest. I have here the three giants of Amazon, Netflix, and Twitter. And you can see that they are simply Death Stars of complexity. No human can look at that and say, oh yeah, I can totally understand what Twitter is doing. In fact, when Elon Musk took over Twitter, nobody in Twitter could explain to him how Twitter works. But it doesn't have to be that big. Even in your typical software system, the level of inherent complexity is such that we have far exceeded the ability of the human brain to make sense of it. Nobody can maintain it, nobody can understand it. And the proof is in the pudding. According to Google, up to 85% of all software projects fail. Now, I think that it is at least 85%. Why do I disagree with Google? Simple. Our definition of success is different. My definition of success is meeting your commitments on schedule, budget, zero defects. The industry is doing so poorly, it has had to redefine success, because when you're out of shape and you have to jump over a bar, you can do two things. You can either get in shape and jump over the bar, or you can lower the bar. Now, people are so incompetent and so reckless that instead of getting into shape and recognizing that they have no idea what they're doing, they lower the bar. Success in software is defined as anything that doesn't bankrupt the company right now. Now, you can bankrupt the company later. You can fail the business by being unable to change. But if something leaves the building missing an arm and a leg and a bleeding eye 2 or 3 years later, and millions of dollars over budget, that's considered success in software today. Now, 85% of the projects fail to meet even that low bar. And that's the present day situation. And as bad as things are today, wait until you see the future. We are facing the need to address a next generation set of problems. Problems in energy, in finance, in defense, in IoT. And the industry, with its poor track record, can simply not do it. And so if they cannot do a simple business system, how could they do a complicated one or a complex one? Not only that, but a hallmark of the next generation systems is a need for resilience. Everything has to be resilient. It means being able to function at some reasonable level in spite of really bad things happening all around you. Now, while the industry keeps trying to lower the bar, businesses keeps raising the bar. However, let me suggest to you that the system design goals I started with have remained the same. And in fact, even more so. It is even more crucial with the next generation set of systems to design simple, to be able to respond quickly. Why? Because of the size and the cost and the criticality of those systems. If those systems misfire or do things bad, we are no longer talking about a user losing their tweet. We're talking about whole economies collapsing. And so while the system design goals remain the same, it is even more important to adhere to them. And at the same time, the industry cannot handle it. Now, a word about terminology. I've used the word complicated and complex so far several times. And indeed, most people use these words interchangeably, but they are not interchangeable. So let me define complicated and complex. Complicated means something that has many small parts with very intricate details of how they interrelate to each other. However, you still have deterministic behavior and know exactly what it's going to do. Complex, on the other hand, means unpredictable outcomes. It has nothing to do with how many parts you have. And even tiny, tiny changes in the boundary conditioning, tiny changes in the system have monstrous effects somewhere else. And complex systems typically feature emergent behaviors. They behave in a way that nobody could foresee, or even nobody could even tell if it is a correct behavior in advance. So let me demonstrate that. A clock is complicated, but it's not complex. Think about all the little gears and the springs inside a clock or a watch. It's definitely complicated, but the one thing you cannot say about a clock is that it gives you non-deterministic results. A minute from now, it will show me exactly a minute from now. A computer is complicated, or at least the hardware is, but it's not complex. There's probably more parts here than in a clock, but everything here has known input and output, known outcome. Everything here is highly regulated, the voltage, the clock, and so on. Now, most software systems are complicated, and I would argue often needlessly so. For example, here is a project from an iDesign customer, and this unbelievable mess is very, very complicated. In fact, this is the fourth iteration of the company trying to implement a system. And this was the fourth back-to-back failure for that company. They've spent untold number of millions with up to 40 developers trying to make sense of this. I was able to show them how to build the system with this. Now, clearly, if it was possible to do the system on the right, then the complicated mess on the left was needlessly complex. There was no really business value for making it that complex or that complicated. And in fact, while they've spent close to a decade on 4 failures back to back trying to do the one on the left, the one on the right took them 18 months. Ooh, and it took them 18 months with 4 developers, which is 10% of what they've spent so far. So most software systems are complicated, but often needlessly so. But now let me show you something complex. The double pendulum is complex. And it's complex because there is no way of predicting or calculating where it's going to go as a function of time. And you can see here a simulation of a double pendulum, and you can see that it's going all over the place, sometimes even above the original pivot point. Now, on the left, you see the physics governing its motions. This is 10th grade, sort of like junior year in high school level of physics. It's not complicated physics. It's very, very simple physics, and yet nobody can understand what is going on. Nobody can predict it. Nobody can calculate it. And every time you run the simulation, it will do something else because the difference is in the 18th digit of the floating point or something. And even that tiny digit causes unbelievable changes. Here is the Chua circuit. The Chua circuit is a collection of very simple electronic components, and yet you cannot predict the voltage in this circuit. And if you try and predict it, it gives you this crazy chart you see here. And it is astonishing that something as simple as here that contains two resistors, two capacitors, and a coil result in this unbelievably complex behavior that nobody can predict. In fact, here's what it looks like if you run it in an oscilloscope. It can't even keep up with what is going on here. Here's another example. Any kind of dynamic between predator and prey, consumer and producer, is complex. And in fact, the math governs it is trivial. So what does it mean? Suppose we're talking about a population of bunnies. And bunnies like to reproduce. That's basically the alpha. And of course, bunnies like to reproduce a lot. And so alpha could be very large over here. But at the same time, we have foxes. Foxes also reproduce. And the population of bunnies and foxes govern each other. Why? Because if there's too few foxes, now the bunnies start reproducing. And the foxes say, well, good time, let's make more foxes. They make more foxes, which cut down on the population of bunnies, and now the foxes don't have anything to eat, and so on. Well, if you're going to try and predict what would be perhaps the steady state of this population, where it's going to end with how many bunnies and how many foxes, it turns out that is impossible. You see on the right a plot of the size of population of bunnies as a function of alpha and beta. And there is no way of you calculating and say, oh yeah, it's definitely going to be that number. In fact, crazy things coming out of this. For example, what happens if you eliminate all foxes? Well, if you eliminate all foxes, then the bunnies are going to reproduce and eat all the grass in the world, and all the bunnies are going to die. And so to survive, the bunnies need the foxes. And you cannot intuit this kind of a thing just by looking at the equations. It's very, very complex what is going on here. Now, people have found these behaviors in thermodynamics, in money supply versus interest rate. Any kind of a dynamic interaction of consumption and production has this behavior in it. And you will never be able to actually predict what is going on here. Here's another example of complex behavior, and that is three bodies orbiting each other. Even if you put them at the vertices of an isosceles triangle and let them go because gravity is pulling them together, you will never be able to predict what these three bodies are going to do. It's impossible. You can't say how fast and where they're going to be over time. And every time you run the simulation, it's going to be different because changes in the 38th digit are making it behave in a completely unpredictable, complex way. Now we understand the difference between complicated and complex. It doesn't get any simpler than these three orbiting bodies, and the equation governs it. You can understand using ninth grade math. It's Newton equation of gravity. It's trivial. Now, when it comes to complex software systems, deliberately complex software systems were actually rare. It's not that we didn't have complex software system. We absolutely did. But the complexity was an unintended side effect of the system. It was definitely undesirable. And for example, you see here on the right, the FAA software that controls airplanes in the US. Now, the one thing you don't want to see here is unintended, unpredictable behavior, because that typically ends up with craters in the ground and hundreds of bodies. So that's not good. And yet, this system is actually unpredictable. In fact, 2 years ago, this whole system came down because of a tiny, tiny change in the messaging, basically a text messaging system that airplanes have. and that took down the entire system. Now, complex software systems in the past were complex, but it was unintended complexity, incidental complexity. They were complex because they were simply too big. And we know that complexity is not linear to size. At some point, something that didn't take down the system in the past would take it down now. For example, if you look at snow mounting on the side of a mountainside, at some point, a snowflake is triggering an avalanche. Now, the same snowflake at less amount of snow would not trigger the avalanche, but at some point, any snowflake will trigger the avalanche. It simply has to do with the time it's been in existence, and the longer it is, the more complex it gets, with the number of connections that it has, with the interoperability with other systems that feeds it information or it reports to, with a whole set of legacy systems, some of them written long time ago and nobody's around to maintain it. And with many, many parts. I mean, in the case of the FAA, think about all the control towers and all the airplanes and all the interaction between them. So especially at the edges, there's an explosion of parts. And you put all of these things together and you get complexity. But again, this is unintended, undesirable complexity. Now, in recent years, we see the emergence of a new type of software systems. And these software systems cater for fundamentally complex business systems. And this is a new kind of complexity. This is a complexity that's actually part of the business. And what we see here is incredibly diverse environments that have to deal with an insane number of devices and platforms and APIs and technologies, with a very high volume of interaction between the various parts, with very intense feedback loops between the various parts of the software, and definitely emergent behavior, where how the system behaves is not something that anybody can foresee. But in fact, the emergent behavior is actually a desirable aspect of the system. Another aspect of this kind of system behavior is that there is no understanding of the correct behavior, even under the same condition. So if you take some kind of condition, you ask the domain expert, what do you think the system should do here? The domain expert says, I don't know, it can do this, it can do that. I can make a case for both of these. Maybe there's a third outcome. Maybe there's infinite outcome of correct results, and they're very different results. And the question is what to do with complex businesses, or in fact, what to do with even complex and complicated businesses. Now, again, while I said that complex is very different from complicated, there's no cosmic law that says you can't see them side by side. In such a situation, the business inherently desires an emergent behavior. And the reason is, it's the best approximation of life. If we agree that good software always mimics reality, and we can call reality the business, and the business, the way it behaves, has to reflect the outside world of the business, the real world. Well, it turns out that the real world is highly non-deterministic, and it is an emergent behavior. For example, if you take all the ingredients of a cell, a biological cell, all the water, the fats, the potassium, all the things that makes all the protein inside, and mix them in a test tube, are you ever going to get a living cell? The answer is no. Why? Because life itself, even at the cellular level, is an emergent behavior of those things, which is why nobody has ever been able to create a single living cell. But living cells create themselves a living organism, which life at the organism level is also an emergent behavior. And those organisms interact in a group, which the group itself behaves very differently than the individual, which is also another level of emergent behavior. So if you want your business to interact with that, the business itself needs to have emergent behaviors. And so the business inherently desires the emergent behavior. The business desires a high degree of diversity so that it can actually fit itself into every possible interaction of reality. Now, in such an environment, the business requires even shorter cycle times than before. So what is a cycle time? A cycle time in manufacturing or in business is the time it takes you to do the following cycle. Something changes in the real world, you detect it in your business, you respond to it, you develop the response, you test it, you deploy it, and the whole thing starts again. Well, in such a dynamic environment as what I just described, you want shorter and shorter cycle times. Arguably, you want real time, meaning that it takes no time at all for the system to respond to the change. And the only way to do it, by the way, is to respond at the edges, because if you have to flow the information all the way from the edges to some kind of a center, respond to it and come and go out again, this will take too long. And by the time you respond, the world has changed too much and you're going to be out of phase with reality. And so now we understand what the business inherently requires this emergent behavior. Now, there's another problem here, which in a complex business system, the mere introduction of the software system drastically changes the business, because having the software system opens up new executions that were simply impossible before. It changes the expectation of the users about what is possible, which means changes their behavior, which changes the way they interact with the system, which changes the way they want the system to execute in the first place. So now the introduction of the system has changed the business. The change in the business causes a change in the software. And this is the mother of all feedback loops. And if you are going to try and code it, you're going to fail, because this happens too frequently at too many places across the board. Now, that's already inside the system, but the system interacts with the outside world, which is inherently dynamically and complex as well. Think about the interaction that that system has with the systems of the vendors or the system of its customers. And the system also has to respond to what the competitors are doing, because the competitors are not resting on the laws, they're responding to what you're doing as well. And maybe you have some partners, I'm doing this part of the business, you're doing that part of the business. And of course, above all, we have the watchful eyes of the regulators, and the regulators are always out of phase with reality. So they're trying to regulate what the system did in the past. And so you have to somehow comply with regulations that doesn't apply anymore to what the system is already doing, and on and on and on. What are you going to do? Well, you know what you should do? You should mimic reality. And if good software mimics reality, then now what happens, the software must import the complexity of the business. And the question is, what do you do with that complexity? Well, fighting complexity by throwing more people on it, more software components, more conditional logic doesn't work. Why? Because there's not enough time or developers to even do the first version. Even if you could freeze time and say, let's assume it's not going to change between the time I start development and finish development, which of course is nonsense, because it will change greatly. That will not be good enough. Why? Because there's just too many use cases and you don't have enough time to build it. And in such complex situations, different customers behave so differently, it's effectively different systems. What are you going to do? And even if you solve one particular problem, that solution introduces new problems somewhere else where you thought you actually solve other problems. You'd be literally fighting a hydra, where chopping off one head makes 2 or 3 other heads sprung up. But there's another second order effect problem of trying to solve the problem like this. And that is, if you're going to try and solve it by throwing people and code on it, you're going to have lots and lots of software components and software subsystem. And simply the size of the number of components that you have in a software system makes the software system itself complex, independently of any underlying business complexity. So now what? And the more complex the software system gets, it becomes impossible for developers to understand it, to reason about it. There's no way for customers to say, yeah, it's doing what we expected. There's no way for domain expert to say, well, it's right, it's wrong. Another second order effect is quality. In such a highly complex software system, you will always have poor quality, because quality is always the casualty of complexity. Then you have the human resource crisis. You will not be able to find people that can actually understand or reason about the system. And yet the outside world wants you to write software to handle that kind of complexity. So that's pretty bleak, but every cloud has a silver lining. And the silver lining in this case is basically saying the following. If we have a viable business, which is fundamentally complex, the business also has to handle the complexity. So how is the business doing it? And it turns out that for the business to be viable, in the face of such insane complexity, there has to be some kind of an overarching structure or interaction, or structure and interaction. Now, this is something that is an empirical evidence only. It's based on my observation of seeing such systems. It's not, I can show you a formula that says it has to be so. But if the business is still viable and it can survive and even thrive in such a complexity, it typically has these two things, the structure and the interaction, which means you must take both and make them part of your system architecture. So what does it mean when I'm saying some overarching structure and interaction? When I'm saying some overarching structure, it tends to be some kind of a hierarchy of participants or nodes. I'm going to use the words nodes and participants interchangeably because I mean actually the same thing. A node is something that participates in the hierarchy of the business. Now, at each level in this hierarchy, participants can be similar in size, in their needs. And I'm saying similar, I'm not necessarily mean identical. They can even be identical, but they don't have to be. Now, across levels in the hierarchy, the participants can vary greatly. Now, why is that good for you? It's good for you because you can start sorting participants, and you sort them based on their size, based on their requirements, based on their needs, and even based on how they interact with the business. And at each layer in the hierarchy, you have basically similar participants. And this kind of sorting of participants to places in the hierarchy contains the diversity across all participants, because now at each level in the hierarchy, you only have to handle that type of participants. I know there could be many other variations, but they're not in this layer, so I don't have to care about it. And you basically start containing the diversity. And containing diversity is really good for reducing complexity. For example, suppose we have an airline that has to service lots of routes, and these routes have different distances and different frequencies of how many times a week the airline has to fly there, and how many passengers fly on each route. And so not all airplanes are the same. Some are better for longer routes, some are better for shorter routes, some can carry more passengers, some require less certified pilot and such. But now imagine the airline trying to schedule airplanes and pilots and maintenance across all possible routes and such. This is a diabolically complex problem, right? Think about all the maintenance schedule, all the pilot rotation schedule, all the pilot training, all the mechanics that have to be somewhere, all the possible planes with the different spare parts and different oils and such. Oh my God, what does it take to manage that? Now compare that with an airline that only operates a single airplane. And that single airplane is not the best long distance airplane. It's not the best short distance airplane. So it's probably inferior at everything it does compared to the dedicated plane. But think about now about the challenge of managing that business. It's orders of magnitude simpler because all the planes are the same. All the pilots can fly all the planes. All the maintenance schedule are the same. And now you have a handle on containing the complexity. And you did that because you reduced drastically the diversity. Now, the structure in theory has no beginning and no end, but in practice, there are going to be boundaries to the structure, and those are going to be the boundaries of the business, where the business ends. Now, no system is a complete island, so you're going to have to interoperate with other businesses. And so what you can do is you could also account for the structure of the outside entities. Now, in such a case, the interop node is simply just another node in your structure, but that one deals with the outside world. And of course, you can have multiple interop points. And then once you understand that, you can actually extend the structure to also represent your vendors, your customers, your competitors, your partners, your regulators. Now, it doesn't even matter if they have that system or not. You can actually relate to them and actually make them part of your model of the business, which you model the business in the software. Another advantage of a hierarchy in a structure is that it reduces the number of moving parts. It actually maintains a logarithmic ratio between total number of levels in the structure and total number of participants. For example, suppose at each level you have only 10 nodes. But by the time you have 7 levels in the structure, you can handle easily 10 million nodes. Now, a hierarchy is a classic tool to reduce the complicated nature of the task. And it doesn't handle complexity directly. It does it indirectly by actually handling the complicated nature of the task. Now, if you combine the hierarchy with reusable components, that is a further reduction in the complicated nature and by extension by complexity. Why? Because if the components are actually reusable, and you can reuse those components across all levels in the hierarchy, now you have recurring patterns and you get to reuse the testing effort, and it's easier to reason about the system. And it's also easier to change the structure, because if all the components are really the same, then it becomes a very composable design. And it's easy to extend the structure to do things it wasn't designed to do. And in fact, if you combine a hierarchy with reusable components, now it's very easy for you to keep track in the structure about the changes in the business. Now, for that to actually hold, the components themselves have to be highly, highly modular. And that, of course, will have later on implication on detail design. Let me show you an example of how you use a hierarchy to contain the complicated nature of the task. Suppose you need to display some kind of a message in a grid of LEDs. And so I have a bunch of LEDs. I can turn them on, I can turn them off. And now I have a grid. This is 8 by 100. And I'm asking you to display the text. Now, the way most developers would approach it, and the way classic computer 101 textbook and universities will teach it, is in a two-nested for loop. So one, the outside loop iterates over the rows, and the inner loop iterates over the columns, so you can do it the other way around. And then you iterate across the grid length and the grid's height, and you turn on and off the individual LEDs. Except, what does it take to write code like this? The problem is that this kind of code is incredibly complicated. There is no way for you to look at the code here and say, oh yeah, it's definitely saying hello world. You cannot. It's incredibly complicated to reason about. It's incredibly complicated to write, and it's incredibly error prone. You're going to get, oh, no, that's not this line, it's this row, it's this column. And it's also very fragile code. Suppose I were to tell you, please change the message. Don't display hello world, display something else. Well, literally all your code is out the window. Yes, the overall structure remains, but all the heavy lifting is out. You have to completely redo your code. What if I tell you, yeah, keep the message, but I want you to change the size of the letters or the font? All your code is out the window. And what if I tell you, keep the message, but I want you to add more letters, basically more columns? I'm saying, you know what? I want you to actually have larger letters. So 8 by 8, I want you to do it 10 by 10 or 12 by 12. And what if I want to have several rows of message? Now you're going to have another for loop from 1 to k or something that basically now is iterating over the rows. Oh my God, who can write such complicated code? Who can understand it, right? It is incredibly complicated. So now let's solve exactly the same problem, but this time using a hierarchy. The most primitive element in the hierarchy is going to be a single LED. And what I can do with the LED, I can turn it on and I can turn it off. That's all I can do. So it's very easy to write that piece of code. I take that LED and I create a grid. Let's call it a character. And the character has a very simple input. It's an ASCII character. And it converts it, in this case, to 64 instructions, because it's a grid of 8 by 8, to display a particular character. And of course, if I want to change the font, I have a different character for that. Then I arrange these characters into a row. Now, the row is also a very simple entity. It takes a string and it chops it into individual ASCII characters, gives it to individual characters. So now, look how simple this code is. In fact, I can very easily look at the code and see exactly what the message is saying. If I want to add more characters, I can easily do it. If I want to duplicate the rows, I can easily do it. So now, by using a hierarchy, we've drastically reduced the complicated nature of the task. And so one handle that these businesses have on reducing the complexity is to use a structure, which tend to be a hierarchy. But I told you there's another element here, which is the interaction. So for the business to be viable, the overarching interaction tend to be some kind of a commercial transaction, some kind of buying and selling to and from somebody. You can think of it of buying and selling a physical product like tomatoes, but it can also be some kind of a service. It doesn't have to be a physical product. Now, these transactions can be between participants at the same level or across different levels, or perhaps even both. In these kind of interactions, there's no constraints on how and who initiates a transaction. The participants can initiate the transaction by finding themselves in some kind of an open marketplace. So it's as if going to the farmer's market and somebody is selling tomatoes and you're interested in buying tomatoes. So you go to the tomato stand and you say, how much is a tomato? And if the price is right, you buy a tomato. So you basically initiated a transaction by meeting somebody that either buys or sells in an open marketplace. In fact, the meaning of the marketplace is to bring together, to match the buyers and the sellers. But it can also be a completely private affair. Somehow you have a side deal with somebody who raises tomato to give you tomatoes. Now, there's also a time element here. You can have a transaction for the here and now. I want to eat a tomato now. So you buy a tomato now, you eat it now. But there can also be a future element, which is next week I want to have a tomato. Let me buy now a tomato for next week. Now, the farmer says, well, I'd love to get money now for something I'm going to do in the future. And the farmer says also, if next week there's going to be lots of sellers in the marketplace, the price of tomatoes is going to go down. I can secure now a good price for the future. And that's good. And you would also say, well, maybe next week there won't be any tomatoes. I better secure my supply of tomatoes now. So everybody benefit by having a future commitment. Now note that there is no value in the structure for its own sake. The whole purpose of the structure was to enable these interactions. And so nodes that don't have anything to offer as far as products or services, or nodes that don't have any funds to buy the thing that they need, those should not be in the hierarchy, because being in the hierarchy without being able to transact is pointless. It also implies a second order effect here, that the nodes have to be proportional. So if the node requires a lot of tomatoes, but it can't afford all of these tomatoes, something is wrong. Or if the node promises to sell a lot of tomatoes, but it cannot grow enough tomatoes, something is wrong. And so everything has to be in proportion. What you're buying, what you're selling, you have to be able to stand behind it. And arguably, the node should be able to also function even if nobody provides it the product or the service, because maybe nobody is offering or maybe it can't afford it. And so everything has to be proportionate. It's not just, yeah, I can afford one tomato, but I'm going to now trade in tons of tomatoes. That doesn't work. Now, transactions are absolutely crucial in reducing complexity. And the fundamental reason is that it eliminates every other interaction. Remember that one of the roots of complexity is the sheer number of possible interaction. They need to interact with all of them. They need to understand them and account for them. But by having just a transaction, all of a sudden, all that thrashing is completely encapsulated. Nobody sees it. Now, we don't care why somebody wants to transact, but is it buy or sell? All we care about that they want to transact. And so all of that internal knowledge, nobody sees it. Nobody actually sees also the lower levels, because you can also transact across levels. You don't know how big or small is the underlying level. You don't know who participates. As long as they want to transact, that's all you care about them. You can also start reusing components, because if all you care about as far as interaction is the transaction, then the components that facilitate the trade and the utilities that support the trade become basically reusable component. And as we've seen, reuse is key in reducing the complicated nature of the task. Now, what I just described is the segue into something else. And that something else is called transactive resource management. Transactive resource management is a technique to manage resources based on their economic value. So what does it mean? Suppose you do need to manage resource, and the resource can be data, can be information, can be professional service, can be money itself, any kind of a product. Trying to manage the supply and demand and when and how much and such by using algorithms alone is incredibly difficult. It's very, very complicated. So instead, you don't do it. Instead, what you do is you let the transactions manage the resource based on the economic value. Now, it doesn't actually matter if what you're trying to manage doesn't have a known economic value. You can absolutely assign a value. And you let the marketplace set the price, be it at the present or in the future. And then you allow the free market to dictate the actual behavior of managing the resource. And in such an environment, there is no overall program that manages. There's no central control that manages this whole thing. Now, if there is no overall program that manages the resources, then there cannot be any complicated logic for managing the resource. And that's really the fundamental reason why transactions are a great way of reducing complexity. Now, this is not new. This is what Adam Smith already identified in 1776, and he called it the invisible hand. Somehow, markets, which are inherently complex, I mean, you would argue that the economy itself is the most complex thing we can ever handle. And yet we have participants that don't understand that complexity and don't care. All they do is they do their little part in it. And somehow the invisible hand of the free market equalizes everything and makes them behave correctly. And so basically we let the free market dictate the behavior. There is no overall program that manages anything. Now, almost everything can be a resource. Now, I completely agree with the Beatles that says, you can't buy me love. That is true. But short of that, almost everything else is for sale, be it a product or a task or a service or even information itself. And so the kicker here is that we're going to start building systems that manage resources. It can be anything from physical resources to airline reservations. It doesn't really matter, but we're going to manage it based on their economic value. And by doing so, we're simply going to eliminate the need for any kind of central control, which always leads to incredibly complex logic. Now, this is not a new observation. We know that in the economy, central control is always too complex to manage everything. Now, the reason is called the knowledge problem. Knowledge problem is for somebody to sit there and manage everything in the economy, they have to know at any moment in time and into the future how many tomatoes is everybody going to need and how much they should pay for it. And nobody is that smart. Now, because they cannot know this, central control always resorts to coercion and violence. You will raise those tomatoes and you will eat those tomatoes. And I understand why central control of the economy always ends up in violence. They have to. They have to resort to violence because they don't understand and they don't know what's going on. Now, in a transactive resource management environment, you let the node change its behavior based on price signals. Why? Because if something is too expensive, you're going to consume less of it. And if something is cheaper, you're going to consume more of it. Now, it's actually more than that. Because anytime you interact in the economy, you're making a judgment call. The question is not if something is expensive or cheap. The question is if something is expensive or cheap with respect to the alternative. For example, you don't have to buy tomatoes. You can also raise your own tomatoes. It's very easy to do. Now, there is a price of tomatoes where you would say, I'm not buying tomatoes anymore, I'm raising my own tomatoes, right? So you always compare your own cost of production to the alternative of buying it from somebody else and the time and energy it will require to raise tomatoes, which is part of the equation. You have to take that into account as well. You have to do a true total cost of ownership. Now, if the node changes its behavior based on price signals, there's actually two types of price signals. There's a spot price, which tells you what is that resource or task or product or service or information is worth right now. What is the now price? Now, that price signal, the spot price signals, affects the immediate behavior. But you can also have a future price. And the future price is what you use for planning and control. Why? Because nobody likes surprises. So if you're a producer, you don't want to produce and it costs you something, nothing is free. And then when it comes to sell it, the price is below what you actually, what it cost you. So that's no good. So you would definitely would want to lock now a price in the future to guarantee that you're not going to lose anything. But the opposite is true for the buyer. You don't want to actually buy everything on the spot market because that is the most expensive way of doing something. So you want to secure something because something is better than nothing. Maybe you don't secure your entire demand. Maybe you secure a base level of load that you're always going to need. And anything excess, you are going to buy on the spot. But at least the base load you are going to secure on the futures market. That's a very sensible assumption. That's a very sensible argument in favor of planning into the future. Now, the net result of transactive resource management is an emergent behavior. You cannot look at a set of participants buying and selling a set of products and say, oh, next April, the price is going to be like this. We don't know what the price is going to be. We don't know if there's even going to be a price. We don't know if there's going to be even a supply. We don't know if there's going to be any demand because if the only suppliers and no demand, then what is the price? It doesn't matter. And so not only do we not know that, something else is going on as a second order effect. And that is typically people and businesses don't consume a single product. They could, but they typically don't. And so they both consume and produce multiple type of products. Now the question is, what is the type of product they should consume? And according to Ricardo, what everybody should do is they should focus on producing something they have a comparative advantage. If you can raise tomatoes, it doesn't mean anything. If you can raise tomatoes the fastest and the cheapest compared to everybody else, then you should probably raise tomatoes. Meaning, I know you can do a bunch of things, but focus on the thing that you are very good at or even the best at. And if everybody focus on only doing the things that they are very good at, and they use the proceeds from selling the thing that they are good at to buy the things that they don't have because are less good at it, what we have is the maximum supply of everything and at the best price point. And that is called prosperity. Now, if everybody is insisting on producing everything they need, they're doing a poor job at everything because they're not very good at it. It costs them enormous amount of time and money, so everything is very expensive. Economic activity is next to nothing, and nothing good comes out of it. But the ability to have the emergent behavior here is great because you can also take that. Well, I'm going to specialize in this, so I'm going to invest in this kind of production. So now we understand the two elements of the silver lining. We have an overarching structure, tends to be a hierarchy, and overarching interaction tend to be a transaction, which you're going to use to manage resources. So now let's take this to the next level. Imagine that we can use the same set of components across all levels in the hierarchy. Imagine that for a second. Suppose that you can assert that this is the case. Well, in that case, I would also want to have a relatively small set of components. I don't want to have millions of components, millions types of components. I want to have a small set of components, of types of components, roughly an order of 10 as far as the types of components. So what is order of 10? 8, 10, 12, maybe 20. It's not going to be 4 million, okay? A relatively small set. And we typically tend to group components into subsystems. And we're going to have an order of 1 or subsystem. What is order of 1, 2, 3, maybe 4? It's not 17. So imagine I have this small set of components and a small set of subsystem, very small set of subsystem, that I can now reuse across all levels in the hierarchy. That will give me the ultimate reduction in complexity. Now, of course, this requires having the right structure and the right interaction. There's a lot of provisos that have to go into making this happen. But if you do have that, we already know that that will be the best in reducing the complexity. But if we truly have the same set of components, then we have a high degree of self-similarity because every layer in the structure is very similar. And when you have a structure with a very high degree of self-similarity, we call it a fractal. And we call it a fractal because at any level you look, you see exactly the same pattern. Here is the Sinofsky triangle, a very famous fractal. So you can see that the pattern here of this triangle is repeated here, which is repeated here and repeated here and infinitum, right? And of course, even this triangle could be said is part of a fractal. So at any way you look, at any level you see the same thing, it's called a fractal. Now, in a fractal, there's no way of actually looking at a particular point and even knowing where you are. For example, what if I were to tell you that this triangle is actually part of another Sinofsky triangle? You couldn't tell me that's not the case just by looking at it, okay? And this goes up and down to infinity. Now, in a software fractal, I really mean that all the nodes have to be identical. Same architecture, same detailed design, same implementation. All nodes have to have identical interfaces, same data contract, service contract, message contract, storage schema, all the infrastructure to support them. Everything is to be exactly the same. Now, does it mean that all the nodes are the same? And the answer is no. Because while the nodes have identical architecture, detailed design implementation, they absolutely can differ in the resources they manage, in how they configure, in their policies, in the workflow they execute. And so now, given that the node has to differ in these things, since we understand that we have to do volatility-based decomposition, we also know that the architecture is going to have to encapsulate these volatilities. Now, in a software fractal, each node is unique. Even though its code is identical, it's still a unique node. And it's going to have unique aspects that only this node has. Now, those aspects you don't capture in code because I already told you the code has to be the same across all nodes. So if you capture the difference in configuration and policies in code, the nodes don't have the same code. And if the nodes don't have the same code and you have 10 million of them, nobody can maintain it, nobody can extend it, nobody can understand it. So what you want to do, in fact, you have to do it. You capture the node-specific aspects using a non-developer tool. So we're talking about some kind of a configuration tool, some kind of a workflow engine, some kind of a domain-specific language, or maybe even custom domain tools. And let me show you an example. In the energy project, we have this tool. Now, this is an end user tool. This is not a developer's tool. And the user is actually unaware that what the user is doing now is authoring a workflow. So this is actually a workflow engine, but in disguise. We don't want to confuse the users with terms like workflow engine. We just ask them a very domain-specific thing to do, which is actually configuring a workflow. And it's not even, it's just basically an information. And then we basically take that information and we literally compile it into a workflow. That's a better way of saying what is going on here. And while the number of components is relatively small, the number of possible implementation is open-ended. That can be astronomical. If you look at all the possible configuration value, all the possible policies, all the possible workflows, we're talking about, in the energy project, a number that's probably larger than the number of atoms in the universe or something. It's just totally astronomical. So what this lets you have is behavior diversity, not code diversity. Code diversity is absolutely evil. You want to have a smaller set of components that you can reuse everywhere. Why? We don't like code diversity. We like behavior diversity. You should enable the business to configure everything till the end of time. Now, of course, there have to be safeguards. You can't do this, don't do this. There's safety, scalability issues. Yes, 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 yes. But inside that sandbox, you can play. Now, a number of good things happen over here. And that is, first, you let the business or the business people at the edge that truly understand the business do it. You don't have to actually escalate all the way back to developers to code it. And that means much faster cycle time. And remember, everybody wants cycle time. Now, if you look at this kind of a software fractal, the program is not in any one place. There's no way for you to say, haha, that's where the code is. No, there is no single node that manages the fractal. There is no the manager, there is no the brain, there is no the system. The closest thing you could say is that the program's execution is the ongoing, never-ending transaction across the fractal. And what it takes to support those transactions, because if you're trying to sell something, you have to produce that something. So you have to have some code to produce that something. And of course, by the way, when you're buying something, you have to do something with what you bought. But nobody sees that across the fractal. All they see is transactions. Now, I said that the program, to use the lack of a better word, is the ongoing, never-ending transaction across the fractal. But that's in theory. In practice, there has to be a start and an end. And so starting and stopping the fractal is a special case you have to deal with. The result is a massive non-linear reduction in the complexity of the system. All of a sudden, all you have to do is get a single node correct, not 10 million nodes, not astronomical number of interaction. You don't have to deal with any of that. Just get the ability of the node to buy something and sell something correct, to produce or consume something correct. That's all you have to do. So the fractal lets you have your cake and eat it too. On one hand, you have incredibly simple system design implementation. On the other hand, you can handle a very complex business situation without importing the complexity of the business into the software. Now, it is incredibly easy to model the business. All you have to do is do it one-to-one. See what the business is doing. Don't try and invent things. Don't try and be uber smart, and just mimic that interaction in the software. So it's incredibly easy to reason and model it. And it's also easy for non-software people to do it. Next, what you have is you've managed to contain changes to be local behaviors. And those things are cheap. The first reason they're cheap is that you don't involve developers. And developers are very, very expensive, not just because they're expensive per hour. They do that, but they could also even unintentionally break things. And that's even more expensive, right? Now, of course, they never issue a refund for the defects they themselves have introduced, but put that under the integrity and morality portion of the problem, not a technical problem. Because you don't involve developers, it's by definition cheap. And it's also fast because you do these very quick in situ cycles at the edge. You don't bring them all the way in and have to cycle back out. And the changes are contained. A node can change its behavior drastically, and nobody else at the fractal, the same level above it, below it, knows that. All they see is perhaps a change in how it transacts with the outside world. Everything else is fully contained. So now changes do not ripple across the fractal. And that's a key idea. Why? Because I mentioned to you that one of the key ingredients to complexity is ripple effect. We change something and it causes ripples, and those ripples change other things which cause other ripples, and those ripples on top of ripples on top of ripples create insane level of complexity, and really bad things happen. But now nothing ripples across the fractal. Now, while the nodes are small, the fractal can be absolutely huge. In fact, in the energy project, in 13 levels, we can actually model the entire US from the light bulb and up. So that's a huge fractal. Now, again, there is no code, there is no script, there is no sequence for the actual behavior of the system. You basically stand it up and let it rip. You don't have to write that kind of code. You can't test it anyway. What's the point? Now, the aggregate behavior of all nodes in the fractal is by itself an emergent behavior. And you don't try and model that behavior in software. You let that behavior be. To use an analogy here, suppose I let you I'll give you a task, program me an ant. Well, that's a classic task today in AI, program an ant. Sure, here's how the ant, and it walks, and it picks up food, and it follows a trail of the pheromone. Great. Could you write for me an ant colony with millions and millions of ants? Probably not. And the reason is the colony doesn't behave like 7 million individual ants. The colony behaves like a single new entity called the colony. And the nature of that behavior is an emergent behavior of aggregating all the individual ants. But there is no program inside the mind of the colony. There's a program inside the brain of a single ant. But what is the colony? It's the emergent behavior. So basically, as soon as you get 7 million ants together, you get a completely different entity. So that's kind of like what you're trying to do here. Now, the fractal lets you maintain your ability to respond quickly to changes in the business. Even very large businesses, if you model them in a software fractal, you have an incredibly fast response time. And being able to respond quickly to changes in the business is the essence of agility. Agility is not the useless ceremonies. It's being able to respond quickly to changes. And that starts with having the right design. Now, in a software fractal, in order to respond to changes in the business, you only change the local behavior of nodes. And it can be some high-level node, but you still only change the local behavior of a node. And those changes you can do very, very frequently. They have no ripple effects. They're incredibly cheap. So the software fractal encourages you to make those changes. Now, you could, in theory, also change the fractal topology itself, how the structure relates to itself. But those things, while you could do it, are fairly rare. And the reason they're rare is the structure of the fractal is a product of the business relationships. And it turns out that business relationships change much slower than the business behavior. So they could change, but typically at a glacial pace. And so your need to change the topology of the fractal would also be much reduced. Now, of course, it's very easy to change the topology of the fractal. You're just wiring things in a different way. You still don't change any of the code. Okay, so nothing changes in the nodes, even when you change the topology of the fractal. Let me give you some examples for these software fractals. The first example we're going to discuss is sorting numbers. Sorting numbers is a classic exercise in computer science and software engineering. And the professor says to the student, write me a sorting algorithm, and then they all do bubble sort. And bubble sort is very, very similar to that grid problem with the LEDs. You have two for loops, and you do bubble sort and such. Now, besides the execution complexity, it's very complicated code. And its complexity as far as execution complexity is very high, it's n squared. Now, the more sophisticated one would write some kind of a binary tree. Now, trivial binary trees are trivial to write, but we know they don't work unless you have a balanced binary tree. And a balanced binary tree is a very complicated entity to run, and you still get roughly n log n. So as far as execution complexity, it's not great. Let me show you a fractal way of sorting numbers. We're going to define as a very basic atom a single component that can compare two numbers. So it takes two numbers and outputs over here the smaller of the two, and over here the larger of the two. That's all it's doing. So this is, a one-line piece of code. It's not a big deal. So this is trivial to write, absolutely trivial to test, and say, yes, it's working correctly. So now I can take 5 of these and use them to sort 4 numbers. And here's why it works. Suppose I feed it 4, 3, 2, 1. Then the smaller of these two is going to be here, and the smaller is I'm going to basically wire these into this comparator. And the larger is going to be here, larger I'm going to wire the two. So basically, after this one executes, I have the smaller of the 4 here, and after C4 executes, I have the larger over here. All I have to do is sort the 2 in between. So here it is. So now I've compared 4 numbers using components that were only good to comparing 2 numbers. Well, I can view this as a unit for comparing 4 numbers and use it to sort 8 numbers. 8, 16, 16, 32, 32, 64, 128. In no time at all, I can sort all the numbers in the universe because it's exponential. But think about it. This is incredibly simple to write. Oh, by the way, these sort numbers in an order of one, except it's not exactly one. We still have the overhead of filling in the pipes of feeding the numbers into it. But after we do that, it's basically an order of one, which is much faster than n log n. Not only that, there's a recurring pattern in the fractal. This is a true fractal. Think about it. Here I have 5 components wired up this way. Here I have 5 components wired up exactly the same way. So we even see a recurring pattern as you go up the fractal in the way you set up the fractal. That's a bonus. That's cherry on top. You don't have to have that. But now I've taken a single component and reused it ad infinitum. Next example, let's talk about the power grid. Today's power grid is like your classic software system. It's highly monolithic and it's incredibly fragile. And we cannot introduce renewable energy at scale. And the reason is renewable energy is intermittent. And the grid has to be at constant balance. Every watt puts on the wires, you have to consume somewhere. Well, if the renewable energy is intermittent, the sun is on, the sun is off, it's windy, it's not windy, the grid is destabilized. And in order to stabilize the grid, you basically have to take out of commission long-running power plants because those you cannot turn on and off on a dime. And so the plants that you took out are basically the cheaper plants. So now you have incredibly expensive power sources. Any economy that tried to base itself on renewable energy has more than quadrupled its power price. When you quadruple the power price, kiss goodbye manufacturing. Kiss goodbye any kind of economic activity. You can view the economy as a black box. Energy comes in, some GDP comes out. Well, if you have expensive energy comes in, you're going to get expensive GDP comes out, which means you're non-competitive on the world stage, which means no prosperity for you. Same goes for electrical vehicles. A vehicle takes as much power as a house. About 70% of power consumption goes into residential houses. And so if mommy and daddy each has an electric car, we need to triple the amount of power production. You think any politician has budgeted tripling the amount of power? Of course not. We typically produce the power far away because nobody wants to see giant chimneys or giant windmill or millions of solar panels in their front lawn. So we put it far away and then we send it to the city. But to send it to the city, we have to traverse long distances. And so what do? We transform it. So even if it's manufactured at, say, to 3,000 volts, we transform it up to 500,000 volts, go the distance, and then transform it down, 210 or 220, because if you have 500,000 volts going to your house, everything is going to arc, and that's no good. Okay, even if those transformations are incredibly efficient, the average watt is transformed 11 times. And so now you lose 30 to 50% of the energy. You could say, hold on a second. I know everything you said. This is why we're going to use grid storage. Grid storage is a laughable insanity. If you take a city like San Jose, California, which is a modest-sized city, it's not New York, it's not Mexico City, it's not Seoul. If you take a modest city like San Jose, it requires $750 billion, so $750 billion of storage, and it's a recurring cost every 3 to 5 years. The money for it doesn't exist. I'm not talking about the rare minerals in the Congo, which requires millions of slaves in Africa to produce, which of course nobody talks about that. I'm not talking about that. I'm just talking about the fact that the money to pay for the batteries doesn't exist. Now, in addition, the energy in the grid is not consumed or produced uniformly. There's peak production when everybody come home from work, turn on the lights, turn on the stove, turn on the heating, or turn on the AC, turn on the television. There's a monster spike. And then towards midnight, everything comes down and the grid is basically at half of what it used to be at the peak. So how do you actually balance that? So now you have picker plants that actually can turn on a dime. And you had base, but we took away the base because we introduced renewable energy. So now everything is a picker. So picker is actually inherently inefficient. In addition, it takes time to start and stop it. So in many countries, they just let the pickers run continuously. And so you don't have to actually spin the turbine. It's already spinning, and then you throw the switch. Well, that's inherently very wasteful, and pickers are not as efficient as the bigger ones. And so that's more cost. And the more pickers you have, the more complex the grid itself becomes to the point it can't take it anymore. And that is what happened in Spain this summer, where all of Spain was completely in the dark and untold number of billions of euros were lost because of these problems. Now, everything I said so far, we could have actually still handled. And we could have done it because energy was relatively cheap. Unfortunately, we're moving into a world where energy is going to be expensive. How expensive? Unbelievably expensive. How unbelievably expensive? Well, Germany has basically shut down its industrial production so it can actually keep the lights on in the cities. That's how expensive. And so we're going to have to transition into a different way of managing the grid. And that model would require local production, local storage, and local management. And by transitioning to managing the energy locally, you avoid the waste of sending it over long distances. You also have a far better knowledge about your own needs. So you're only going to produce as much as you think you're going to need, not as much as maybe the grid is going to need. And you can incorporate local generation. And the most important thing is to be resilient. And resilient simply means that you're going to maintain an acceptable standard of living in the face of great upheaval in the wider grid. So the name of the game here is actually how to be resilient. Well, this is not a new idea. And you all heard about a concept called a microgrid or a smart grid. And a microgrid is actually a node in a fractal. And the reason is a microgrid is a grid of microgrids. So it's a microgrid of microgrids. Each one of the nodes in the grid both has load and production. And the node manages its own power locally, but it can also participate in the market of buying and selling. And you can maintain this fractal all the way from the individual light bulb into a building that has a collection of these devices, into a neighborhood, a collection of buildings, into town, which is a collection of neighborhoods, into a city, into a country. So the energy factor looks like this. Inside a building, you have its load, things like appliances, refrigerators, and such, but also its means of production, solar, perhaps battery, a generator. And every building has that. And we group these buildings into a microgrid. But we could also have microgrid level resources. And resources are good to compensate in case the individual buildings have a problem, but perhaps we have buildings that don't have anything besides load. Maybe microgrid level resources would service those. And we group all of these microgrid along with other microgrids, and we group that into cities and everything else. In such an environment, each node can predict its need for power or its surplus of power, and it can publish it. And it can actually say, I'm willing to buy this much power, and I'm willing to sell this much power. And it can buy and sell power on the spot, but it can also buy and sell power in a future market. And the individual node now becomes resilient to grid disruption, because even if the overall grid goes down, perhaps this subsection of the fractal is still up and running. People are still buying and selling from each other. So what? So bigger grid is gone. They are still okay. If they bought enough power from each other and they have enough to support, they'll be fine. Now, they may have to change their behavior. That is true. But something is better than nothing. In such an environment, you have exactly the same code in the individual device, individual refrigerator, or even a light bulb, to a building, to a city, to a country. And Each node is perfectly fine standalone. Remember, I told you before that it has to be also proportional, and that's what gives you the resilience. And what I just described to you is the EnergyNet project. And while this kind of a system sounds incredibly complex and challenging, a small team of 5 developers and 1 architect has done the full implementation. I'm not talking about use case analysis and all the pre-development. Has done the entire implementation, including testing and documentation, in about 2 years. So it is a far superior way of actually spending time and money of development resources. And it's arguably the only way of tackling the insane problem of energy as far as complexity. Now, again, each node is incredibly simple as far as external behavior. It just buys or sells. That's all now. Inside, there's other behavior, how it reaches those decisions. We're going to discuss that. But external behavior, very simple. Next example I have for you is a next generation command and control system for the military. Here's a screenshot I took in 2017. The future of the US military is constructing a giant armed nervous system. The cyber chiefs are converging on a single strategy for military dominance. Connect everything to everything. Okay, what is going on here? Think about managing a war. Think about all the soldiers, all the ammunition, all the logistics, all the support, all the intelligence. Oh my God. That's already inherently complex problem. But it turns out that complexity has dire consequences. First, you think the army actually knows exactly where everything is all the time? Probably not. Now, they're getting much better at it. During the Second World War, the US military didn't exactly know how many planes and boats it has anywhere. I mean, they knew more or less, but not exactly. So how do you compensate? You compensate with overcapacity. You send more because who knows? They didn't know exactly when every plane had a malfunction or was shot down or a boat was sunk. Then you eventually, but not immediately. So you have to compensate with overcapacity. But even if you know where everything is, you still make mistakes. At least 1/3 of all the casualties in the Iraq and Afghanistan wars were blue on blue, where US troop was shooting on US troops, or British troop was shooting on Australian troops. Oh, there's some bad guys over there. Call an airstrike on them. Boom. Oops, that was our guys. Oops. And so imagine a world where every bullet is smart and every rifle is smart. So if you point the rifle at one of the good guys, the rifle wouldn't fire. And imagine every soldier that's smart and all the biometrics and the health status of the soldier is actually beamed back. And the platoon commander has some kind of a visor with augmented reality. And as you move around, you look up, you see the drone in the sky. You look down, you see red triangles where the enemy is. You see blue triangles where your guys are, and so on. Imagine that world. And why stop there? All of this is connected to some kind of a higher level. So now the battalion chief is seeing what's going on, and the airplanes in the sky see where everybody is, and that goes back to the aircraft carriers and so on. That's what they're trying to build here. And though they've been talking about it for a long time, recently they started doing it. So here is a press release from April this year that finally this becomes an official program at the Department of Defense. And indeed, in May, they did this exercise to demonstrate these things. Now, what you see here is the elements of what I talked to you about. So this missile is not just a missile, it's a smart missile. And not just the people in the APC can control it. Somebody here in a different command vehicle can actually designate targets. And here's these things, and you can see they have just as many antennas as they have missiles. And you can see lots of antennas over here. Here is Lockheed's Martin rendering of what this system should look like. Now I can tell you the easy part to build is the hardware and the antennas and the missiles, because that's what they started with, and that's easy. The difficult part is all the lines in between, because that is also a software factor. It's actually a multi-dimensional software fractal. We're going to discuss what that means. And if all of this sounds familiar, some of you should have a weird sense of deja vu because I think we've seen this before. Because this sounds like pretty much like Skynet. Of course, they're building Skynet. In fact, an iDesign customer is the contractor for building this, and they even call it Skynet because, it's a good name. Next example are supply chains. Supply chains are inherently fractal by nature. There's a famous exercise that let you do in an MBA school where they say, write all the steps required to manufacture a single pencil, and please stop after 5 million steps or 5 million points in the supply chain, right? That's inherently a factor because everything that goes into everything has its own supply chain. And every one of those things has its own supply chain. So it's supply chains of supply chains of supply chains. So it's inherently a fractal concept. Now, what's interesting in that is that there's a very high degree of self-similarity in these supply chains. For example, here's on the left the supply chain of computer equipment, some motherboard, and on the right, some cosmetics. I mean, at this high-level overview, they look almost the same. Now, I can tell you that even this is actually still somewhat simplified. This is just the first order. If you were to try and look at everything, it looks something like this. So inherently incredibly complex and inherently a fractal. In fact, here's a nice, interesting visualization. This is a research from a research paper on supply chains, and they took one plant in Zhejiang, China, and you see that's basically the red point over here. And in blue, you see every supplier they have across China. Now, what you can clearly see is that they don't have just one vendor, they have, 100. And that's basically what you see here, the primary. Now, every one of those suppliers has their own network, and here's a secondary, and every one of those have a tertiary. It looks like this, right? So if you put it all together, it looks something like this, which is, crazy complex. And in fact, in this research paper, um, and so look at it from the perspective of somebody that tries to manage a supply chain. So how many parts should you order from that supplier? And what if that supplier goes bust? Well, maybe you should have a second supplier. Okay, how much should you order from that second supplier so that you can get, okay, so how long do you think the outage is going to last? And maybe you should actually pay more for a supplier that's more reliable. And on and on and on. In no times flat, managing this kind of supply chain becomes incredibly complex. And guess what? Here's a chart that actually shows the relation between suppliers and consumers. And if this looks very much like the predator-prey rabbits and foxes showed you before, it's because it's very much the same. It's the same equation that govern all of these. Okay, so using a fractal software for managing the supply chain fractal, that's something that makes perfect sense. However, it makes also crucial sense. And the reason is, it's because the world of globalization as we know it is gone. No more is the fact that you can buy and sell anything from anywhere. Those days are gone. Don't take my word for it. Here's The Economist, right? The Economist, basically, we have here the world's map and it's all torn into pieces. And so the world is in the process of splitting into several independent, borderline hostile trading blocks. And between you and me, this was bound to happen. And the reason it was bound to happen because globalization was always very brittle and unsustainable. How brittle? Recall that during COVID, when the Chinese stopped making one kind of a silicon chip, all of, the US car manufacturing grounded to a halt because we're missing one part. So you're missing one part, then you can't ship the car. So they started accumulating tens of thousands of cars uh, because they didn't have one part. Right? Like for want of a nail, the system fell. So it's already incredibly brittle. Now, that makes also sense because if everybody in the world has moved into just-in-time manufacturing, and they have to, because just-in-time allows you to reduce your inventory cost and be very agile in responding to changes in the market. So if now the world wants more trucks and SUVs, you stop making SUVs, you make trucks. And so you don't want to have all the parts in inventory for making all the cars, you just in time order everything. So just in time enables businesses the ability to be incredibly efficient because you basically have no inventory and responding quickly to changes. The problem is if everything is just in time and you're missing a part, you don't have just in time, you're just screwed at that point. So that was always very brittle. But it was also unsustainable. How long, if all the manufacturing goes into China and nobody's making anything in the rest of the world, how is that going to work? How are they going to pay for the products that they're buying from China? Printing money? Well, printing money ended up poorly. So now what? And as you're shipping things across the globe, across great distances, what about pirates? Well, as long as the US Navy was patrolling the seas, pilots kept their head down. But at some point, the US said, well, I've had enough of everybody taking advantage of me, and you should start paying for patrolling the oceans. But if they're not paying, then now you can't send things over long distances. And globalization requires peace, and peace requires uh, speaking softly while carrying a big stick, if you know what I mean. Well, the US is saying, I'm done playing the world's police. You Europe, you China, go and party on. And so it's unsustainable. And the US is saying, I'm done with everybody selling things in the US, but charging hundreds of percent tariff on American goods. That's gone. And so it was always unsustainable. And what we see now, we see the process of the world splitting into several blocks based on the access to key things. For example, each block would have would coalesce around the ability to produce food and to a lesser extent water. And I understand China's mad rush into buying farmland in Africa. But second on the list is energy. We're going to have blocks around access to energy. Just as important is access to microchip, specifically the high-end chips. China can make lots of chips, but they're like third-order chips, are not the really good chips. Those are made in exactly two places, in the US and in Taiwan. And we're going to see blocks around trading routes. And those trading routes can be rivers or ports, but not just access to routes, also the safety of the routes. So you're probably going to see routes that go in between trading blocks susceptible for pirates and attacks. Blocks are going to coalesce around ability to produce basic goods. I'm talking about closures, okay? I'm not talking about fancy things. They're going to coalesce around financial instruments, such as the BRICS currency versus the US dollar. The petrodollar is gone. We're going to see probably the return to some extent of barter in the international market. They're going to coalesce around demographics and specifically access to labor. For example, the US needs Mexico because the US population is aging and the Mexican population is not. And so access to plentiful younger workers. And we're going to see coalescing around military capabilities, especially around the need to protect the shipping routes. And this is why now Japan is building the world's second largest deep blue navy. Why? Because they're going to have to start projecting their power across the Pacific to protect the shipping routes leading into Japan. But it's going to be a lot easier if they coalesce along with Taiwan, if there is Taiwan, South Korea, Thailand, Singapore, probably Australia as well. So that could be one block and so on. We're going to see this kind of fracturing. Now, each block is today scrambling to rebuild the supply chains. Everybody understands what is going on, and everybody is in the process of retooling their economy to secure their needs. And this involves, for example, in the case of the US, reindustrialization. So the US is now transitioning from a service economy to a manufacturing economy. And each block is going to move into regional production as opposed to consuming from remote places. And each block is going to definitely prioritize resilience over efficiency. Yes, I know you could do just in time and incredible efficiency, but that's not very resilient because if you're missing one nail, the whole thing is gone. So now we're talking just a reduction in the number and types of products. They're going to be much more basic with a higher degree of interchangeable parts. So they're going to be resilient to supply disruption. Let me suggest two books on the future of supply chains. James Rickards Sold Out and Peter Zind, The End of the World is Just the Beginning. Both have different takes on exactly the same problem, describing this rebuilding of the world supply chain. So anybody that's going to be active here in next generation supply chain management, they're going to be having a good time with a fractal architecture. And think about, as you're designing that supply chain, how many parts to order? Should you have two suppliers or one supplier? What's the lead time into changing the order? All of these things are incredibly complex, and we're going to need software to answer all of these questions. More fractal examples. Any kind of software that tries to predict the market, emulate the market, interact with the market, would benefit from being fractal simply because markets are a fractal. You all heard about the IoT, but I was one of the first in the world to talk about the IoT. But even then, I didn't talk about the IoT. I talked about something I now call the greater IoT. Imagine trillions and trillions of connected devices. Now, the reason we're going to build the IoT is not because it's cool and it's interesting. We're going to build it to get a real-time dynamic picture of the world. And so, again, it's a problem of the cycle time. Typically, businesses measure the world, interact with it, and then store it and analyze it and decide what to do and implement the change and roll it out. That takes too long. The best cycle time is to have near infinite sensors measuring the world, and then in real time, analyze those numbers and act on it. That's how we're going to build the IoT. Well, that's actually a factor. Think about managing compute time and storage. Compute time and storage are now becoming a commodity. And it's interesting to see it even at the high-end level. For example, those NVIDIA AI chips, each cost $50,000, are now becoming a commodity, and people are actually renting them out because they could probably make more money letting somebody else use the chip because of the shortage than using it themselves. And that brings into the foreground the concept of a digital supply chain. Think about a software product that requires a lot of storage and a lot of compute power in order to build the AI model, the LLMs, or storage of this thing, right? Okay, that's one thing, but you use that as one building block in somebody else's digital product. So in fact, you know what we have here? We have a supply chain, except it's completely digital. So now imagine buying and selling the compute time and the storage and the bandwidth in between. All of that is a factor. You all heard about the metaverse. Think about a virtual world which is indistinguishable from the real world as far as the ability to affect vision and sounds. And people are going to have work in the metaverse. Oh, yes, I'm going to be making a living. They're going to buy and sell services. They're going to be interop between the metaverse and the real world. Well, we're going to have to build a completely new economy in the metaverse, and the economy is a fractal. So fractal architecture sounds like a good idea. Think about healthcare. Now, what does it mean? If you look at you as an individual, it's kind of weird that you have to ask your doctor to get a copy of your lab results or your X-ray. The information is yours. Why are you asking permission from the doctor? Not only that, that information is used by big medical, pharmaceutical to do research and develop new drugs, but they're not giving you anything for it. Imagine a world where you own all your medical information and you decide for the right amount to buy and sell your own medical information. It's going to be anonymized and everything else, but why not buy and sell your medical information? Why not buy and sell medical services to you? So again, we see the concept of transactive resource management. Think about AI organizations. Today, large companies are using AI ad hoc. So developers are using it to write some code, and people in accounting are using it to do some audits, and people in legal are using it to review some contracts, and people in marketing are using it to write some marketing sentences. So they're all using it a little bit. But now imagine a world where we're using it much more. And in fact, we still have a company, but most of the employees are nothing but AI agents. There's still probably one or two humans in the background, but the entire organization is AI driven. Well, an organization is fundamentally a fractal. We have the individual, we have the team, we have departments, which are lots of teams. We have a company, which is lots of departments. We have a conglomerate, which is lots of companies. That's classic fractal. And they transact in people and in money between themselves and to the outside world. And so imagine we build this kind of a world, but using a fractal architecture. And really, the sky is the limit. Literally, you can use this kind of a mental model to solve pretty much even problems that you initially thought are actually fairly simple. In fact, there's an observation in complexity theory that there are no simple systems, meaning everything is complex. Okay, so now I'd like to discuss some common patterns as you go about building these software architectures. Nodes communicate over a message bus. A message bus is nothing but a queued pub sub. So you create a message and then you can also now broadcast it to a bunch of subscribers or perhaps even one-to-one. You can even do request respond over a message bus. But conceptually, it's a queued pub sub. Well, nodes don't talk to each other directly. They talk over a message bus. Now, a message bus is what connects the various layers in the hierarchy, but nodes also talk to each other over a message bus. But it's important to notice that we actually have here a message bus fractal. What does it mean? It looks like this. So let's look at the top. I have two nodes, and if they want to talk to each other, they post and send messages on the message bus. And perhaps this is one level of some kind of a marketplace and buying and selling things. Now, this node also manages an internal marketplace. And here's a message bus that these nodes communicate. But as far as this node is concerned, this is an internal message bus. Now, this node also manages an internal marketplace, and here's that message bus. And as far as this node is concerned, this message bus is the outside next level message bus where it transacts with its peers. So what we have here is a message bus fractal. Now, a common pattern is that across these levels, you do not make the communication open to all parties. Only select few can go and pick out. And the reason you want to do it is to reduce the number of interaction because you want to contain complexity. Also, another interesting pattern is that every interaction on the message bus is opt-in, meaning every need to know about certain things or to transact is not something that you can say, you're going to transact now. What if they don't want to transact? What if they can't? What if they don't want to? Right? So everything has to be opt-in. In a fractal architecture, definitely go with a closed architecture. Now, that's a good idea in general principle. But because of the inherent complex nature of the problem, you really want to go with a closed architecture so that you don't betray the details of lower levels to upper levels. So node can transact with peer nodes, or they can manage one level down. But beyond that, they don't do anything. Definitely aggregate transaction instead of opening the fractal. So if you want to have a transaction that is like the sum of all participants, don't just sum it all up and make one transaction. Allow the transactional mechanism to progress across the levels in the fractal and give you the result as one big transaction. And that way, you don't have to know the inner working of the lower levels. Another common pattern is that each level maintains an exclusive access to the market it manages. Nobody can bypass that layer and go level up. So what I mean is don't have this node bypass and go into something for this message bus. No, it has to go through this. And this exclusive access is done both to separate the layers, because remember, across layers, we could have different needs, different markets. And so all of a sudden, I push down information about higher level markets and different rules and different policies to levels where they're not really relevant. No, don't do it. If you want to do something up, transact all the way up. You typically have a concept of a market maker, which is what if there are no suppliers and nobody's willing to sell anything? Well, somebody could say, I'll take some of my own supply and I'll sell it for a really high price, but I'm only doing it to kickstarting the market. Or we can have the opposite. What if there's only supply? Nobody wants to buy anything. Well, now somebody can step in and say, okay, I'm going to start buying something. Even though I don't need it, I'll put it on my own storage just to get the market started. Now, if you have access to upper and lower markets, you can do arbitrage. You can see if one of them is buying and selling the same product at a cheaper price, and then you buy cheap and you sell high. And it's a guaranteed way of booking a profit. Now, that is a great idea, not just to make profit, but to also start creating liquidity in both markets. And that's also another reason why you can't bypass the market, because if you can bypass the market, you bypass the arbitraging, and you want the arbitraging to actually start equalizing across the levels. Otherwise, the trading may be blocked. Now, inside the node, you still communicate over a message bus. And on that message bus, you want to propagate transaction. And we're talking the classic ACID transactions. And that way you can actually start engulfing things in broader transactions. I'm talking about classic computer science transactions if you need to. Now, inside the node, regular iDesign method rules apply. So managers, engines, all that jazz stays the same. Nothing has changed in node. And node is just your typical business system. There's nothing special about it. Now, you can see that here, these two nodes communicate with a message bus, but inside a node, you still have an internal message bus. That's basically what these dashed arrows are showing. Another common pattern in a fractal is discovery. It's really a bad idea to have a preordained fractal, this connects here, this connect there, and you always have to be this and that. That's not very resilient. And so the fractal needs to constantly discover the structure. Who is available? What are they willing to do? Where is the market? And you constantly dynamically verify things. Same by the way with status. Is somebody available in the first place? If a device is available, if the market is available, those things you can also do with kind of announcement. Hello, bye, I'm available, I'm unavailable. And then there's no need to pre-configure anything. In fact, the way things start is everybody just boot, and then they use discover, and they use discovery to discover all the parts in the fractal. And once discovery is over, the fractal is basically alive and it's breathing. Another common pattern is for subsystems inside them to produce observable events. So managers, when they do something, they fire an event. And that's a good idea because you don't really want to know which subsystem needs to handle that. You post an event, and if that subsystem needs to do it, they subscribe to it, and they're going to be fine with it. As far as node architecture, here are some common volatilities, things that change between nodes. For example, market rules. How big is the market? What's the time granularity? How long is the time horizon for trading? What is allowed? What is not allowed? All of these is node specific. Market policies. Things like How long do I, the node, want to trade? What is my pricing policy? What is my margin? All of these trading things you need to you need to allow to change between nodes. Every time there's a price signal or something changes in the market, you need to respond to it somehow. Now, how the node respond to it is node specific. Some may choose, if the price is high, to curtail the response. Some will say, well, I don't need to do anything because I'm sitting pretty and so on. So all of these workflows specific to the node. If the node is trying to trade, you have to produce trading targets. How much do I want to buy and at what price, and also at what point in the future? Well, it turns out that the workflow for producing these things is highly node specific. Calculating a price in general is very node specific because each node has its own means of productions, its own preference, its own demand for resilience. Every time you access a device, the device could be different than any other device any other node had. What about some assets like databases or such? So containing some information. So each one of these things could be very different across nodes, and they may use different access to access it. Again, how you store things locally, remote, to what degree, that's all volatile. Same with infrastructure, how the node supports things, how it manages security, diagnostic, logbook, transaction, all of that you need to encapsulate. The clients are also to a large extent volatile because different customers of the Fractal, they want to visualize different things, want to do different things. Some have a higher tolerance for bad things happening, some are lower tolerance, some are risk averse, some are not, some want to gamble, and on and on and on. Now, if these are the common volatilities, since we need to encapsulate the volatilities in services, here's also some common services. The node typically has an exchange to manage the market. Now, this exchange manages the market underneath the node, but it also manages the participation of this node in the market above it. You're going to have some kind of a business intelligence or analysis that deals with the question, do I want to buy? And if so, at what price? Do I want to sell? And if so, at what price? What price? How often? How much into the future? How do I respond to external changes in the environment? And external environments can be parts of the fractal become unavailable, the weather has changed, the interest rate has changed, and on and on and on. All of these things require someone to analyze and respond to. How you manage the resource itself, or the asset, or the information, or the task is also something you need to manage, and you have some kind of asset manager of some kind. How you access the resources, and the resources are there to enable you to support the transaction. How to access the resource itself is also something you need to encapsulate. So in broad strokes, here's the architecture of a node in a fractal architecture. Let's start here. Here we have the asset manager that manages the actual asset that the node has to support the transactions. We have the change manager, like I said, manages the market that this node manages or participation in the market above. Here's some kind of an analysis. Here's some kind of an environment manager that basically manages all the discovery and the events and so on. Here's some kind of a pricing engine. Here's various resource access, enables you to access resources that support the transaction, such as accessing an asset or the marketplace or configuration or your workflows. Here we have some generic utilities, utility, logging, the message bus itself, some kind of diagnostics. And you're going to need one or two of these clients, such as a client that enables you to configure the node, can also visualize what's going on inside the node. Perhaps some kind of a client that manages the participation of this node in the fractal, maybe some kind of a timer that fires timed events. Another interesting observation about the node architecture is that while inside it can have very complicated logic inside the workflows and the analysis and such, what it exposes to the outside world is incredibly simple. We're talking perhaps a single facet with very few operations, and one or two perhaps subscription facets subscribes to outside events. That's it. That's all the node needs to expose to the outside world. Now, again, you can have very simple outward-facing behavior, but very complicated internal behavior. So again, note my language. The node itself can be very, very complicated, but the node is not complex. The node is always deterministic in how it behaves and how it responds things. Overall, the fractal can be incredibly complex, but not the individual nodes. And remember, all the coding effort goes into what's happening inside the node. So you basically don't deal with any kind of complexity. Definitely follow a closed architecture. That's always a good idea, even inside the node. And the node is always some kind of a smart hierarchy. The node has no business value standalone. All the business value is not by having a single node. It's in the composability into the fractal. That's where the business value comes out. The node tend to execute a series of discrete use cases. Each use case is incredibly simple. Do this, do this, do this, you're done. Here's some input, do something on it, you're done. But what these use cases tend to do, they tend to come in a string where you constantly are responding to these events coming from the system. Now, the overall business workflow of the node is the progression between the queues separating the individual managers inside the node. Now, again, there's also a message bus between nodes and their managing nodes. So what you see inside the node is you see a manager taking a message from the internal bus, doing some processing, put it on the bus, and that gets posted perhaps to another manager that picks it up, does something, puts it back or not, and keep going. And this keep going forever. But separately from that, we have the message bus across the nodes where the managing node posts messages here, and then they interact with that message. Now, node B is completely independent from node C. It doesn't even know that there is a node C. Now, a part of the fractal is still a fractal. And so the node doesn't need the entire fractal. Its subtree of the fractal, its sub-hierarchy is probably good enough in many cases. And in fact, not only does it not need to, the node must be fine on its own, meaning if at any moment in time the node disconnects from the fractal, it should be able to continuously operate. And you have to design the fractal so that nodes can connect and disconnect. Now they can connect and disconnect themselves, or maybe the entire thing that they sit on is disconnecting. They don't care. And that is how you support resilient architecture. Resilient architecture is one of the hottest buzzwords in the software industry today. Everybody's talking about it. Why? Because we're moving into a world with great adventures, and you need to be able to operate in the face of degrading environment. And so how do you support that resilient architecture? And you just saw it. You have a fractal architecture where each part of the fractal, all the way down to individual node, can island itself off from the rest of the fractal. Now, they can do it voluntarily. They choose to disconnect, or somebody disconnects them. It doesn't matter. When it happens, you need to detect it and respond to it. That alone, just what I said, is a reason to use a fractal architecture, even if we didn't have all the other problems the fractal solves. Just what I just told you right now. Just this. Now, as you're building these fractals, there's going to be some components that are going to be interchangeable and reusable. And I call them basically commodity-like components. These are things that there's no business value in them, and everybody should have them. And the classic two components are the exchange itself, meaning your participation in a market should not be different than anybody else's participation. Your management of a market should not be different from anybody else's management of the market. How you set up an environment, how you discover components, how you apply certain policies, all of that, no business value. All the utilities, diagnostic, message bus itself, logbook, security, all of that is just a commodity. It may be a lot of effort to write, but fundamentally, there's no business value in it. The competitive edge and the added value is in the analysis and in how you manage the assets and how clever are your policies and your workflows. That is where you add the value. So you want to spend the least amount of time doing this and the most amount of time doing this. The business doesn't care about that. The business cares a lot about this. Okay. Another aspect of the fractal is when you interoperate with somebody, You're going to have to agree on a certain interface. You're going to have to publish it. Okay, that could betray some internals. And so your internals, first of all, should not be the business of anybody else. But even worse than that, there could be a trade secret. So it's not a good idea to mix in the interoperability endpoints your way of analyzing and responding to things. That's not a good idea. So always be aware when you are designing these interoperability, what are the things you want to expose? What are the things you most definitely want to keep hidden? Now, when it comes to structuring the interactions themselves, there's some interesting guidelines. The best is to transact locally in real time. If you can satisfy everything you ever need using transaction in the here and now, you're perfect. Why? That gives you the ultimate just in time with maximum knowledge. You don't have to speculate. Maybe the price is going to be more expensive, so I better pay extra now. But no, I know what the price is now. If the price now is okay, use it. So if the price now is always okay for you, that's fantastic. You also don't have to speculate on your own need. Forget about the price. If you say, well, maybe in the future I'm going to need some of this, I better buy it now. Here and now, I know exactly how much I need. And I also know exactly how much surplus I have. I don't have to speculate, well, maybe I'm going to have some surplus. Let me sell 80% of it. No, I know exactly how much I have. No 80%, sell the whole thing. So you have the ultimate just in time with maximum knowledge. So that's why transacting in the here and now is always the best. That will minimize your costs because you're not going to have the overhead of either not selling all the things you would be able to produce or buying more than what you would actually need. It would give you a faster cycle time. It will definitely reduce complexity. Looking at what you need to do here and now is typically less complex and trying to predict all the future and what it has to store for you. And there's really no coupling here. It also maximizes the privacy because if you transact locally, the information about you and who you are and what you do doesn't travel very far. And if all you need is the people next to you, then by and large, everybody's more resilient if they behave the same. Second best is to transact locally, but for later use. You're saying, look, I don't have anything to do with this piece of information or product now, but I'll keep it, I'll store it later for later use. Not as good as being able to immediately use it, but still good. The third best is to transact somewhere where somebody else views the resource more than you. And so that somebody else can be at the same level of view as the hierarchy, or across different levels, basically the market above you. Now, obviously, this makes sense because, yeah, I would like to use it, but someone's willing to pay me so much for doing it. You know what? I can do without tomatoes. Hey, you have the tomatoes. You're willing to pay so much for it. But not only does it make economic sense, it also increases resilience because when someone is willing to pay a lot for something, they really need that something. And if they really need that something, they can't operate without it. So by you willing to give up on something by hoping to help somebody else, you increase overall resilience. And we already discussed that fundamental aspect of the fractal is resilience. It also means if you operate according to these three guidelines, that transactions tend to dissipate across the fractal. Meaning, suppose I interact with my peers and I'm buying something, and suppose I'm buying 8 tomatoes, but I just want 5. So I have 3 extra tomatoes. What do? Well, I'm going to sell it upstairs. Somebody else there says, well, I only need 2 tomatoes. Maybe I sell 1 upstairs, or I sell 1 to my peers. So what happens here is that if you follow these 3 guidelines, transaction tends to dissipate across the fractal. The longer they get away from their point of origin, the less they get as far as quantity and as far as granularity, time granularity. Another interesting observation here is the nature of the transaction across the levels of the fractal. So I have here aspects, and I'm going to describe here what happens as you go down the fractal to that aspect. So the first is the product granularity. So it turns out that at the top of the fractal, we're dealing with very large quantities of the product, whatever it is, all the information. And first of all, it makes perfect sense because if the top is the aggregation of everything that happens downstairs, and of course, the top will have the largest granularity. And to use an example, if you're looking at the power market, say in your country or even just in, say, in California, it's dealing with hundreds of megawatts. But you at the very edge of the fractal, the house, are dealing probably with individual kilowatts. Okay, that's 1,000 to 1 ratio in the difference in granularity. So as you go down the fractal, the granularity increases. By the time you get to a light bulb, it consumes individual watts. Temporal granularity tends to decrease. So at the very top, you're only going to be willing to deal with very short time horizon, the next second, because of the knowledge problem. You don't know what's happening downstairs. You don't want to speculate what happens going to happen a minute from now or a week from now. So if I know what's happening a second from now, I'm willing to take that chance. Now, as you go down the fractal, as you go down, the knowledge increases. By the time you get to the edge is perfectly aware of what the edge wants to do. And so as a result, it's willing to deal with shorter and shorter, it's willing to deal with longer and longer units of time. So it's willing to buy power in longer periods of time. And the same goes with the time horizon. At the top level, you're saying, I don't know, I want to deal with what's happening next week because I don't know what's going to happen next week. So I'm only dealing with tomorrow. But down at the fractal, you absolutely know that next week you're going to have a party and you need to buy a lot of tomatoes for the party. So you have knowledge, and because of that, you're willing to do transaction into longer and longer time horizons. The number of transactions tends to decrease as you go down the fractal. And it has to do with the depth of the market. By the time you get to the edge, there may not be any other players. It's just you, maybe another node. So how many tomatoes can you buy and sell? Not a lot. By the time you go to the top, there's the aggregation of everything, and you can actually balance at the top. So it's a very deep market at the top, and it gets shallower and shallower and shallower as you go down the fractal. Predictability definitely increases. We discussed it. Because of the knowledge problem, the lower you are, the more knowledgeable you are, and therefore you can predict for longer and longer, and your prediction also have a higher quality. At the top, you can only say, it's going to be hot in summer. Okay. At the bottom, you can say, well, it's true, it's going to be hot in summer, but I'm going to be doing a trip in the North Pole, so I'm actually better take a sweater, right? So you have knowledge at the bottom, which is give much higher quality to your predictions. Resilience tends to increase as you go down. And it makes sense because if every node can support itself standalone, that also is true as you start aggregating things. But at some point, you can say, I've aggregated the whole thing, right? So the whole thing can still come down, but the individual parts are still resilient. And that means that the whole is less resilient than the parts. So as you go down, resilience tends to increase. Interestingly, the number of nodes tend to stay constant, but in a small range. So 4 nodes, 8 nodes, 12 nodes, it's not going to go to 12,000 nodes. That's not a good fractal. In a good fractal, you have a structure. If you have 12,000 nodes, that's a flat grab bag of everybody. That's not a fractal. So a core aspect of the fractal is that the number of nodes per layer is fairly small. Now, because of the logarithmic nature, as you go down, you keep multiplying and multiplying and multiplying. That's how you get the multiple nodes. Price tends to increase. And think about it. If you're buying and selling something, if you're buying in larger quantity over a long horizon of time, you are going to get a better price than if you're buying little quantities, right? And because the quantity tends to decrease as you go down, price has to increase. But the same goes with time horizon. If you're buying, remember, at the top, you're not willing to do longer term transactions because of the knowledge problem. But at the bottom, you're willing to actually do it because you know what you're going to need. And as a result, if you go longer on a time horizon, the price has to rise because you're asking somebody to defer their consumption or even to store the product for you until you're ready to take possession of it or use it. And therefore, the price has to go up. So as you go down the fractal, the price goes up. Another aspect of the fractal is reliability. The fractal must be reliable. Now, reliable is not the same as guaranteed delivery. Reliable means guaranteed knowledge. So what does it mean? When I post a message on a fractal, every message has exactly two outcomes. The message gets there and I know about it, or the message doesn't get there and I also know about it. Maybe the message got there. How do you program against maybe? Usually the message gets there. How do you program against usually? Almost certainly the message got there. How do you program against almost certainly? And so it has to be a non-deterministic outcome. Without it, instantly all the complexity of the interaction is going to come and explode in your face. Now, this is something transactions help a lot. And in fact, inside the node, everything should be transaction. Now, something bad happened, like network went down and such, transaction was back, nothing happened. But also transactional queues, because I could do a bunch of things inside my node, and then I want to talk to the other node, and I'm posting it a message, but it goes into a transactional queue. If anything bad still happens on my side, the transaction queue is going to reject the message, and it is as if it never happened. And if I have a transaction queue, once the message gets there, dequeuing it starts a transaction. It goes to the other side, enlists the incoming queue, commits, and the message gets there. Anything bad happened, the message queue on the other side rejects it, and the message reappears on my side for another delivery attempt. Now, of course, you're going to have to have workflows. What happened if they had trouble figuring it out? But even the handling of the poison are also transactional in nature. Now, delivery may take a long time. Who knows how long it will take? And even if delivery was instantaneous, the node could be down because, bad things happen. So don't design that you actually depend on knowing when things exactly happen. The node can any moment in time can go up, down. You don't care. You don't depend on it. Now, when it comes to delivering messages, you have to handle failure to deliver. So if I post a message to somebody and the network is down, now what? Well, maybe I should retry. So let me try it again. Now, you have to manage the retries, because if I'm doing retry, I give up, that's probably not as smart as doing a retry and then 10 minutes from now another retry and then 20 minutes another retry, because I'm giving the network time to come back, or I'm giving it time for the machine or the cluster to reboot, or whatever it is. And so you have to manage the retries. Of course, infinite retries is also no good. So you start looking at time to live on each message. You say, look, if it takes more than so many minutes to the message to get there, I'm not interested. But you can also compensate at the tender level. You could say, look, I'm willing to try and buy something, but if that doesn't get there or doesn't contract in the next 10 minutes, I'm canceling it, auto canceling, right? You can put this kind of expiry on the business meaning of the message in the first place. Separate from that is, even if we were able to deliver it correctly, it failed to execute. Maybe it tries to access some kind of piece of information or resource that's unavailable and it couldn't do it. Well, again, same rationale, maybe you should have a few retries. Except now there's a problem. Somebody could attack you by designing a message that you can never succeed processing and basically exhaust you by keep retrying and retrying and retrying. It's like doing denial of service on yourself. And so what you could do is you could do some kind of poison handling. You could say, look, I'm only willing to try for so long and so many times. And if I cannot do that, I deem it as a poison message and I move it to a poison queue. And then I have a separate workflow for handling the poison. And all of this means you need to have dedicated failure workflows, failure to deliver, failure to execute. All of these needs to be part and parcel of your workflows. You also need to be able to handle a black start. A black start is a node starts up and there's nobody home. No other node is available. What do you do? Well, first of all, in the name of resilience, you must be able to operate standalone. Start operating standalone, but then you still need to try and contact the outside world. Now, if somebody is available, perhaps a peer or a node above, you start interacting with them. Now, remember that every piece of the fractal is a fractal. And if every node is doing it, and every piece of the fractal is doing it. That's how you solve the black start. So handling the black start is actually a fractal solution as well. So the black start of the fractal is actually done in a fractal way. Avoid long-running processes. Yeah, I guess it will work. It would compile, it will work, but why are you doing a long-running process? Um, and besides, if you're using transactional queues, the time it takes you to dequeue it, start a transaction, and it could actually outcome that transaction. So if you want to use a long-running workflow, don't tie the incoming message. Dequeue it, commit that transaction, and then kickstart a long-running process to do something with that message. Process messages as they arrive. Don't do another level of buffering that buffers the message and processes it. No, just keep it simple. Definitely process one message at a time, so you won't have to deal with reentrancy issues and with synchronization issues. And sometimes you're going to have several messages of the same type. Well, you need to perhaps detect it and then process just the latest one of them, so you don't have to actually process all of them. As far as technology, your technology stack should support the following. Distributed transaction, of course. If it's doing transactive resource management, it sort of needs to do transactions. I already mentioned transactional queue. I'm going to mention it again. It's so important. But it's not just transactional queue. What you want to have is transactional queued services. Because the one thing you don't want to do is handling the messages in a raw. What you want to do is you want to maintain the service-oriented programming model of interfaces, where you have an interface on operations, and then you have a technology stack that converts these method calls into messages that go into transactional queues, and take the message queues, dequeues them, and convert that to a message call, to a method call on an interface somewhere else. So you maintain almost a C#-like programming model, but in fact, the underlying transport is a transactional queue. If you can get that going, you're in a very good place. Already mentioned reliable messaging. Every time you post a message, there's a known outcome. You need to support message security. HTTPS is not secure. And if you disagree, talk to the NSA and Snowden, and they will tell you how non-secure it is. You need to encrypt the message itself. But you need to have a technology stack that does that, because otherwise you start infusing your code with ugly plumbing. So you call what look to you like C# methods, but in fact, it's an encrypted message that goes over the queue to the other side. I already mentioned to you discovery, but I'm also talking about discovery and announcement. So the system constantly is discovering the various parts, but you don't have to write that code. Let the infrastructure do it. Message bus. Unfortunately, most message buses today off the shelf are no good. And so you're going to have to typically write your own message bus or customize to a very high degree an existing one. Support for long-running workflows where something is coming in and then a minute later there's another message and such. Yes, yes, yes. You need to deal with massively concurrent. In the fractal, everybody is shooting messages at everybody else all the time, and this time is kicking in. You need to be able to handle it. And so everything needs to be thread safe in your technology stack. The stack must support online work and connected work. And because any moment in time, in order to be resilient, you have to handle the fact that the network could be down. So what do? You support offline work. In fact, the only way to actually do it is to program as if you are never home, meaning the network is always down, and you deal with that. And there's a private case when you are actually down. Another aspect of technology is domain-specific frameworks. Most technological stack are inferior. And the reason they're inferior is because of the enormous span that most vendors face. If you look at the span of development skills, it's probably 1,000 to 1 between the best developer in the world and the worst developer in the world. So if you're a technology vendor, what are you going to do? If you target most people, then maybe that's most of the market, but then the entire high end of the market can't use it. If you target just the high end, select few can use it, but then the most of the market can't use it. So what do? You aim for the middle. So you got sort of okay things, but not much, which means you need to augment the existing framework, be it .NET or Java or whatever it is. And the best way of augmenting it is with domain-specific extensions. For example, if I were to tell you I wrote a program where everything is an object, you're saying not so good because it's not type safe. Okay, what if my program is using a lot of floating points? Well, if you use a lot of floating points, you're back in object, except now it's a floating point object. And the problem here is you lose type safety. So if I have a very simple formula, velocity equals distance divided by time. So that's the formula, and I'm writing velocity equals distance times time. It compiles, it's just floating point, except it's the wrong result. Imagine your framework knew about velocity. And now it wouldn't accept anything besides distance divided by time. So in the energy project, that's exactly what we did. We developed a framework that restores type safety on floating point, but based on domain constructs. And the same argument about a zero dimension, basically a single float, has to do also with collection. If I have a collection, a list, or an array, or any kind of a collection, I typically don't have it for the sake of collection. I have it because I want to manipulate it in some way. Well, imagine that the way you manipulate it is also domain specific. For example, if I have a list of prices and transaction, one times the other is the total cost. So imagine that collection is aware of it and has a property called cost. Or in the case of the energy, if I have a curve that basically is my meter reading, the integral of that curve is the total energy I spent. And out of that, I can actually also generate a bill. And so what you see here in the screenshot is a framework that sits on top of a framework. So this framework gives domain-specific meaning to the collections in .NET. So we don't actually have to deal with things like array and such. No. We have these wonderful collections, and all the operation we'd ever want to do is actually domain-specific. And this framework sits off on top of another framework that gives domain-specific context to floating points. So in fact, the entire project doesn't have just floating points. Let's talk about events versus timer things. In a Fractal, you constantly respond to outside events. And so naively, I would say, let's make everything be event-driven. And as a first approximation, that's fine. And now everything happens concurrently to everything else, you respond to events. The problem you run into is that some use cases are periodic. For example, the marketplace is giving me a price tick. Or at the end of the month, I had to collect everything and send somebody a bill. Okay, so those things are timer-based. And now you have to deduce timers. You say, okay, I don't like that. So how about I use timers for everything? And even if I have events, actually first go into a queue, and then I'm going to have a timer that actually goes and pulls the queue. Yes, I guess you could do it. Except now the programming model becomes very complex because you have different timers and they're not perfect harmonics of each other. They're not like 8, 4, 10, or whatever. And then whatever then, because 4 doesn't divide 10 and you have to do the things in between, and it becomes an ungodly mess. And so very quickly you regret ever using timers in the first place. So in practice, here's what you need to do. Use event-driven whenever you can, and use timer-driven whenever you must. Another twist in the tail here is that the fractal can and often is multidimensional. Now, a dimension can be an aspect of the business or a product or a resource you're selling. What does it mean? Suppose I'm buying and selling tomatoes, but also buying and selling corn. Well, I can't sell corn in a tomato market. That doesn't make any sense. And so each one of these dimensions is a different dimension of the business, which has a different service or a product or a resource. It has a different marketplace, a different set of prices, and a different time granularity and such. And the fractal can be multidimensional because the same node can participate in different fractals to satisfy different needs it has for different products and services. Now, in such a world, each resource has its own marketplace and its own granularity. By the way, even if it's the same product, for example, if we look at power, I can have the 1 second market where I'm buying and selling power on a second by second, but I can also have a whole day market. Well, I can't sell individual seconds on a 1 day market. So it's a completely different market with completely different rules, even though in both cases you're selling power. Now, You can also have the one-day market for power, but here I'm sending megawatt, here I'm sending kilowatts. Again, not interchangeable. So any kind of change in granularity or in time granularity requires a different marketplace or different dimension of the fractal. But again, it can be a completely different product. And that means that the marketplace can actually overlap. They can overlap across the nodes, they can overlap across time horizon and time granularity. Because even if it's the same product and it's the same granularity, is it for the next week or is it for the next year? Oh, that's actually a separate market over here. Now, you absolutely want to overlap the dimensions because that is another reduction in complexity. Because suppose I'm dealing just with power, but I have to deal with power over the next second, power over the next week, power over the next day, power in kilowatt, power in megawatt. All of a sudden, trying to do all of that is incredibly complex. So what do? We use exactly the same technique. Again, we break it again into marketplaces and we let transactive resource management manage each dimension on its own. Now, obviously, dimensions can actually interrelate. For example, suppose I have transactive water management. Well, I'm buying and selling water. Fine. But in order to buy and sell water, you're going to have to pump it. But pumping requires power. So all of a sudden, my transactive water requires transactive power management. Suppose I have a supply chain and I have transactive parts and I'm buying and selling parts. But that actually requires transactive yield management. So if I have a factory, I also have a program there that uses the factor of the factory to optimize the throughput of the factory. And so that all of a sudden I have to interrelate with the transactive parts system. In the military, suppose I have a bunch of fighters, and the key concept is called time over target. You want to maximize the time over target of planes as far as if a plane is spending 99% of the time going to the target and back, that's not very efficient. I mean, sometimes you have to do it. But at the same time, the more they're over the target, the more susceptible they are to getting shot. That's no good. So there is some happy medium. Okay, so now suppose I have a bunch of planes, and each plane has a different amount of fuel and different amount of bombs remaining, and they're all flying to the tanker. That requires not just active fuel management because who do you fuel first? Based on what? Based on how much fuel they have remaining? Well, maybe they only have one bomb remaining. Let me fuel the one that has more bombs left, but less fuel, and on and on and on. All of a sudden, we have transactive fuel management, and the Skynet computer is going to have to manage time over target along with fuel management. Now, you encapsulate each dimension in the node. And nobody from the outside needs to even see the node is participating in multiple markets. That's implementation detail. And then you manage each dimension on its own in separate marketplace. A key aspect of the fractal is simulations. Simulations are so crucial to the fractal. I would even say, you say fractal, I hear simulation. Why? Complexity. The fractals are so complex, you cannot just look at it and understand what's going on or even teach yourself. So what do? You use simulation to understand and demonstrate, to prove ideas, to demonstrate to other the concepts. This is crucial during development to even say, are we even on the right track? Would this actually be a good idea? Well, let me simulate it and see if it would make a good idea. I'm not going to wait till the end of the project. Also, post-deployment. Simulation is a great way of commissioning a system and seeing what it's doing, and also saying, okay, this is what the system did. We can run simulation to see what it should have done. Is there a problem? Is it acceptable? How do you answer these questions? Now, because of the complexity involved, simulation are really your go-to tool when it comes to developing workflows, to developing policies. Is this too much? Is this too little? When should I do it? And even to design the fractal, there's always going to be near infinite ways, we're going to talk about it, of designing the fractal. Who says one way is better than the other? I can make a case for either one. Okay, so instead of having them in all one big string, let me make it in 4 different levels, each with 2. Okay, is that better? Well, I mean, now the market are getting shallower, but now I'm getting more flexibility. So I'm trading number of transactions with flexibility and on and on and on. Who knows what one is better? We don't know. So we're going to simulate it. Simulation also makes sense business-wise. People love to spend money and jump ahead. No, before you commit the capital or even the resources, the human resources, to go and do something, simulate it. Simulation are much cheaper than buying hardware. Simulation are much cheaper than assigning teams and giving them budgets. Simulation are much cheaper than doing expensive trial and error or renting stuff in the cloud and paying through your nose and saying, well, this fractal design costing us an arm and a leg. Maybe we do this fractal design instead. It reduces the number of messages and the compute time or whatever. Simulation are great way of reducing the integration risk. Because of the number of parts involved here, what are you going to do? Write all the code and then bring everybody together and integrate it and hope it's going to work? It will never work. So you constantly, even inside the node, you write simulator for the other part based on the interfaces you have, and you integrate against it constantly. So by the time the real component is ready, you drastically reduce the integration risk. Simulation drastically reduce the total time to market, and they reduce the cost all around. I cannot stress enough how important it is to invest in simulations. Now, what do you simulate? You simulate every physical component because you're not going to give every developer an access to a laser gun or a bomber or a power station or a plant or a field of tomatoes, right? That's complete nonsense. You just simulate that. You simulate policies. You simulate an entire deployment environment. Before you even go to the customer for the first time, simulate their environment and proof it on your side. You simulate how the outside world is going to interop with you. Are they going to operate like this? Are they going to send me these prices? How often? What is that going to do? Now, the simulation themselves, the simulators themselves need to be composable. So you start simulating simple things and together you put them together into bigger and bigger simulators. So what you actually obviously see here is that the simulators are also a fractal. And it's a fractal of simulators, and each simulator is itself a fractal of simulators. Here's an example of what this looks like. So here's actually, in the energy project, an entire grid fractal simulation. And this actually uses about 10,000 simulators, and it's doing it from the light bulb and up. So what you see here is an entire city from the light bulb and up. And you can navigate the fractal and up and down. In fact, I have this ready as a demo, so let me just bring it up. Okay, so there's a lot going on here. What you see here is the entire power consumption of a city from the light bulb and up. So this is the aggregate, kind of like in the megawatt range of a city. And you can see here all the things that similar, but I can actually go down the fractal. So if I go down, here's neighborhood 1, and I go one over, here's neighborhood 2, different neighborhood. If I go down over here, here's cul-de-sac 1 inside neighborhood 2, and here's another cul-de-sac, and another cul-de-sac, another cul-de-sac. If I go down here, I see a house. It's an individual house, and I can actually go and see other houses. And if I go down in here I see the light breaker inside that house. And if I go down in here I see an individual light bulb. So what you saw here is an entire city from the light bulb and up. Here is another simulator. This simulates what's happening inside the node. Now, remember, inside the node, things can get fairly complicated. So it's not a surprise that the simulator for a node is complicated, right? There's a lot going on here. You can see here power consumption, solar production, battery discharge, futures. So basically, it's going to buy this much power here in green, and here's going to sell this green and such. There's a lot going on here, okay? But again, from the outside world, they don't see any of this internal complexity. Simulations are crucial during development. You need to model the system. You need to have a coherent model in your head. You need to do a what if. Will this be a good idea? Well, let me try and do this. Did I write the right algorithm? Did I forget a certain edge case? Well, what are you going to do? You're going to simulate the input and see what's going on. Simulation are great in recovering. Okay, so the node disconnected or an entire subfractal disconnected. Okay, it wants to come back. Under what condition can it come back? How does it synchronize with the rest of the transaction that happened? Does it have obligation as far as transaction to things that happened when it was disconnected? How do you deal with the recovering of putting back things together? Well, you're going to simulate it. Simulations are instrumental in training operators. The complexity of these software factors defies the mind. And there's no way that an operator would be able to make the right decisions, even as far as configuration, on the first day. So what do? You give them a simulator of their environment and you say, play with this. We don't give you any sharp pencils now. Play with this. You're not going to do any damage. Let's proof your ideas. Get comfortable running the system against a simulator, then we'll let you do the real thing. You also need to invest in simulation management tool. You don't just run a simulation. Every simulation has a value. I tested this, I learned that. I looked at that policy in that context. And so we call these things scenarios. And so each scenario has, here's the overall policies that the various nodes had during that simulation. Here's what we were trying to test. And here's all the things we did. And in fact, you should be able to run the simulation concurrently, because if I'm trying to test this, well, maybe let me test that and that and that. Well, I'm doing all of it in parallel so I can actually see what's going on. Definitely be able to take a snapshot. So I'm taking a snapshot in time of the entire fractal, and I can even save it. And I can then go and analyze what happened. And I can also change some policies and then start the snapshot again. And that means that a simulation needs to have a start and a stop where you start it and then when you end it, but I also must be able to pause and resume things, because when I'm pausing and resume, I'm examining the intermediate results, or I'm even changing things in the environment so I can resume it. So in the energy project, here's the simulation management tool. And what you can see, it's a nice explorer that shows you the scenarios, and you can configure the start and stop and so on. You can create new scenarios. Now, you have to run simulations to test behaviors. It's the height of hubris to think that you're smart enough to know that, oh, this is definitely the right decision in this fractal. You don't. There's always these consequences and unintended consequences of decisions. I can tell you in the Energy project, we are constantly humbled by the system. That the fact that, yeah, we didn't think it would do that. Okay. So the next problem is that some configuration and policies may take a long time to manifest themselves, especially things that would look like they're a good idea initially turn out to be a bad idea in the long run. Or many they're a good idea in the long run as long as something doesn't happen, in which case they turn out to be a bad idea. And so what if this change in trading policy across the fractal will take a year to figure out if it's a good idea or not? What are you going to do? Wait a year? So you have to be able to accelerate simulations. And so in a scalable conclusion, you need a simulated clock. And the simulated clock allows you to accelerate time, but also to slow time. Because of these explosion of events happening across the fractal, things sometimes happen too fast for you to even figure out what's going on. And you can't even put a breakpoint, because with the breakpoint, other things are happening in the system. So that's no good. So what do? How about you slow down time by a factor of 1,000? And now let's step through the system. Great way of doing things. I need to be able to pause things so I can actually go and look at things and sometimes dump it in Excel. By the way, in InterNet, as far as the framework, we also installed visualizers in Visual Studio that visualize in domain relevant ways our collection. So we don't actually paste in Excel and see what's going on. It's all part of Visual Studio. And everybody in the fractal has to use the same clock, because otherwise really bad things happen. So as part of the simulation management tool I showed you, here is a scenario management tool, and you can even tell it, look, I want you to run this simulation for a week. Now it's a week in accelerated time. We're not going to sit there for a week. And I want you to pause after a certain amount of time, because if you hope you're going to be just click the pause button fast enough, that may not be exactly. Maybe I want to pause at exactly a known time. So basically you can even schedule the pauses. And here you can configure the clock. And it says, look, I want to accelerate the clock by a factor of 100. So in that case, 1 minute in the human time would mean 1 hour and 40 minutes in the simulator time. Okay. And you can do at this rate, I already did the calculation, you can do a year in 3 days. Okay. So doing this kind of work, by the way, before .NET 8 was really difficult. In .NET 8, they are finally caught up to the need for doing these things, and there's API in .NET that allows you to swap the clock, and that's exactly what we're doing. So we basically are using what looks like regular system time APIs. Of course, it's not, it's slightly different, but we get the ability to plug the clock. Definitely invest in a fractal design tool. You need to build a fractal. You need to be able to take down individual parts of the fractal. Maybe you have two fractals that operate independently. Now want to join them into a bigger fractal. I need to be able to take them, see what this join made sense for them. What are the changes in policies as a result of me integrating two fractals? Maybe the individual policies were on the standalone version were fine, but now they're part of a bigger fractal. Are they not fine? What are the effects? And if this is a recurring pattern, what are the things to note? Because they could also disconnect. So maybe I need now two policies, one when I'm part of a bigger fractal, when I'm part of a smaller fractal, and on and on and on. So here is a fractal management tool from Nature and Project where we're building these fractals and managing the simulation and the snapshot. Of course, a snapshot captures the entire state of the fractal. A key idea in developing a software fractal is to model the fractal itself. Now, what does it mean? The fractal itself is a model of real-life business situations. And the nodes are going to predict the needs of the actual physical things and perhaps manage deviation because I thought I'm going to need 3 tomatoes. I needed really 4. Okay, so now what? And as a result, the node needs to predict its need into the future. And the question is, how do you do it? Well, the only way to do it is to model the world. Now, the model of the world is often both complex and complicated. There's no shortcuts here. And so in order to handle the complexity, we're going to use the same tool again. We are going to use a fractal model. Again, we use the fractal tool to reduce the complexity all the time. Now, there's two approaches on creating the model, analysis and synthesis. The analysis basically observes the legacy system or any existing system. And often that system is way too complex to analyze by hand. And so you use some kind of AI to analyze what's going on. So it's a black box, but you say, okay, given this input, it had this output. So the AI would say, well, if it has this similar input, it will have this similar output. And that's basically what it's doing to predict new behavior. The problem with this approach is that often the old system is no model for the new. The mere fact that we're doing a new system is because the old system was inadequate in some ways. That's already a problem. And second, I already told you about the mother of all feedback loops, where the introduction of the system drastically changes the business. But this kind of a black box analysis doesn't deal with it. It doesn't know how that's going to actually change. So any kind of emergent behavior is outside the scope of the training. And then when they do happen, it's a big shock and the AI fails and the analysis doesn't work. And so the real downside of doing this, it looks initially like it's not that much work and let the AI solve it because AI solves all problems. The problem here is that it takes a long time to get any kind of good results. The other side, the other option of doing it is to synthesize a model. So what you do is you measure and model very primitive actors at the very bottom of the fractal. And in a fractal way, you model the system and you aggregate them into the hierarchy. And this is basically not the actual fractal, it's a model of the fractal. And often it's a lot easier to reason and relate to when you build it like this. And the reason is very simple. In life, synthesis is a lot easier than analysis. For example, suppose I give you a piece of code and ask you, what does it do? And you would have to spend a certain amount of effort to analyze what does it do. But I could also ask you, give me a piece of code that does ABC. Well, of course, it's a lot easier to write new code than it is to analyze what existing code is doing, right? Because analysis is way difficult than synthesis. So this is actually a far easier model to reason about and to relate to. And there's no black magic, there's no black box. You know exactly why the model did what it did. Easier to relate it, we do it all the time. Now, the downside of that one, it requires investment in the correct modeling behavior. And sometimes, we spent in aggregate about a year modeling one particular behavior. And so, yes, that's a downside. But that was actually an extreme counterexample that indicate the rule. Almost all other models we have are very simple and are good enough. So bottom line, definitely prefer a synthesis-driven model to the fractal than analysis-driven model. And all this brings me to end this session by discussing what I call the fractal challenge. The challenge in a fractal is not in actually doing it. Doing it is amazing, it's rewarding, it's intellectually challenging. You literally get a good dopamine hit when you're working on these problems. That's not the problem. The problem is the problem of the design of the fractal itself and the node detail design. The fractal network design is the problem, not the architecture of the node. I showed you that the architecture of the node is completely trivial. Here's a template, you got an exchange, you got analysis, you got assets, you're done. This is it. That's not a big deal. But also there's no business value. All the business value is all the business added value is in the design of the fractal network itself. That's where the business value is. And so you have to design it correctly. Now, what does it mean? First of all, at the very least, it needs to mimic some constraint in the real life, right? Some interaction, some business interaction between two parties. That needs to be there. But always beyond that, there's multiple ways of representing things. Even for the same constraints, you have to have this line, you have to have this wire. Okay, above that, I can do it like this, like this, like this, like this. Which one is better? And so, because you don't know a priori which one is better, you must be able to reconfigure and configure and test the fractal very easily and very quickly, because if it takes too long and it's very difficult, you're not going to do it. And so the fractal has to be incredibly composable, the ways you're composing it. And you constantly use simulations to identify the correct structure and say, is this good enough or not? This has to involve also domain experts. When you're designing the fractal, you're dealing with the heart of the business. And you don't understand the heart of the business, which means the domain expert has to be involved in every decision. Do I connect it here or there? This is also a highly, highly iterative process. You're never going to get it right in the first iteration. And so have patience and trust in the fact that eventually this churn is going to settle down. A great technique in fractal design is sensitivity analysis. Look at all the things that affect the correct results. With the topology of the fractal itself, how many layers, how many nodes, which node is in which part of the fractal, and so on. The policies of the fractal itself, the policy of the individual node, the policy of the market, the workflows, how each node responds to everything, and of course, the size of things, because if I have this policy if it's this gap, but it's different if it's that gap, and so on and so forth. If it's today or if it's a year, I have different tolerances for things I'm willing to do today versus what I'm willing to do a year from now, and on and on and on. If you're just going to itemize all of these things, you're never going to start because it's just an impossible task. So you have to do a sensitivity analysis. Not all of these variables affect the behavior or affect the behavior the same way or to the same degree. So you literally need to do sensitivity analysis. So, okay, so let me assign to each one of them 3 values, high, medium, low. And let me do some combination of flow here and such. And there's actually tools that do this in a Monte Carlo simulation way, and they zoom in on which variables are more sensitive. And they say, look, yeah, those things matter, but third order, focus on the correct values over here. You have to make the fractal design be part of the testing process itself, meaning it's not okay that it just worked. It's not good enough. Did it do the things in the expected way? And could you have done better? So you have to do that part of the testing. And that's just one challenge in a fractal architecture. The next challenge is the node detail design itself. Detail design is absolutely paramount. Why? Because each node is going to be used across every level in the fractal. Otherwise, it's just a hierarchy. It's not a fractal. And so you have to invest in designing the finer detail of the nodes. And the same node must work not just across all levels of the fractal, but across all dimensions of the fractal as well, which is even a higher bar to meet. And the problem here is that most developers like to code. They don't know how to design. Maybe they like to design, but they don't know how to design. Here, the majority of the effort is on design and not on the construction. The construction itself, if you look at individual use cases, easy peasy. If, else, curly brace, you're done. That's a use case. And this shift from construction to design is a fundamental cultural shift. The entire development culture has to change. The entire management culture has to change. Management have to realize this is a worthy investment. Without this kind of investment, there's no point in even starting. In addition, the detailed design process of the node is a highly iterative process simply because the required behavior of the node is unknown upfront. I would argue it's even unknown at the end because you don't know exactly how it's going to behave, but put that aside for a second. Even under second stage, you don't know what is the right behavior because you could do it like this or like this or like this. And so part of the detailed design process is actually figuring out the required behavior. And you're not used to thinking about it this way. You're used to, oh, here's what I need to do. I'm plucking the user story from the Kanban board, I'm coding it. No, here the required behavior affects the design affects the required behavior because by designing it, you realize that wasn't the right behavior or there's a better required behavior. And so it's a highly iterative process. The nature of the design iterations look something like this. Some domain expert has to write the operational concept. Here is what this thing needs to do. Now, I'm not talking about operational concept for the entire fractal. I'm not even talking about operational concept for one dimension. I'm talking about operational concept for how you manage a particular asset, operational concept of how you do a particular kind of a trade. That's it. Even that can be a very laborious task. Now, no domain expert can ever get that right in the first pass, okay, because the complexity is insane. And so who says who says it's any good? So there has to be like a validation process of the operational concept. And so you need to have some kind of a structured system flow that basically tries to breathe life into the operational concept. Because in operational concept, you can do some dismissive hand wave and not look at something and such, okay, but people have to do it, they have to do it. So merely having a structured system flow, you refine the operational concept. After you do that, you start looking some kind of a mind map of all the possible use cases that this would actually involve. And the use cases are much closer to the required behavior, but who says it's the correct required behavior? So you need to do some Excel simulation. So, and you can do any kind of a good simulation. You can do it even in C#. Excel lends itself because of its tabular nature that each row in Excel is another change in the state of the system. And it's a lot easier to actually go and debug that and see what's going on. Once you have that, you have a better understanding of what the use cases are like, and you develop those. And with those, finally, you can go and do the detailed design. Now, what I just described to you is something that never happens because I described it to you sequentially. But this is highly, highly iterative. Why? Because every time you go a step below, it typically tends to affect the steps above it. So you go down here and then you have to go, oh, well, we obviously, Excel proved this is wrong. So we need to change something fundamental in the operational concept. And then we have to go back to the mind map and on and on and on. You iterate here like there's no tomorrow. Now, eventually, if you do it correctly and diligently enough, and don't cut corners, the dust settles and things tend to settle down, and you got the detailed design at the end. But conceptually, even at the detailed design, you could affect something in operational concept. It's not likely, but it could happen. Let me visualize to you what these things look like. Here is 12 pages out of 165 page of one subsystem in the energy project. So this is not all of the operation concept, it's just one subsystem. And I don't even know how many iterations we had on this document, but I can tell you on the calendar, it took 7 months. Here is a structured flow of another operational concept for another subsystem. And obviously you can't see anything here. So if we zoom here on what you see over here, you see these things. So this is like breaking it down to its most atomic constituents. Here's what a mind map of one subsystem, not this subsystem, a different subsystem, looks like. And here you have all the breakdown into the sub-use cases of that single subsystem. And trust me, you can expand more here. Just we don't even see anything. Here's what these Excel simulations look like. This is actually a full-blown simulator in Excel. It actually is pretty slick. Here is another simulation in Excel. Again, each one of these looks at a particular set of conditions in the system. Here is what various things in the system are doing. Each row here is a different simulation. Here's what the use cases look like. Here you can see the actual activity diagram and a paragraph or two describing it. And we have hundreds of pages, and this is for just one subsystem. Once you have that and you have the detailed design, you capture it in the SDD. And here's what SDD is like. It captures everything public. So every enum, every interface, every class. Here's how you, here's the interfaces, here's what it does, note to do this. Here's the interaction with the other things. We have more than 800 pages of this describing all the details of the system. And this is all up to date and it's correct. And the distance from this to coding is trivial. It's basically, okay, give me this using this. That's it. That's as simple as that. Definitely invest in infrastructure. You don't want to pollute a detailed design with plumbing, with things like security and reliability and transactions. So you need to have this ready-made plumbing that enables you to accentuate out of your code all the ugliness of the plumbing. And I can tell you that in order to be successful in detailed design, domain knowledge is absolutely a must. Now, there's two ways of doing it. One, have a domain expert with you as you're doing it. And the problem here is that the busy domain people are unlikely to commit so much of their time. And the other option is transfer the domain knowledge from the domain expert to the developers doing this. Now, the way to do it is defeat in detail. Basically, what you do is don't expect every developer to actually know every aspect of the domain like a domain expert. That's never going to happen. So instead, each developer should have the developer's area of expertise, managing an asset, doing this kind of transaction, analyzing that kind of a thing. And they specialize in that, and the domain transfer happen in that. And a good portion of it is simply understanding the complex nature of the business. Also make it part of the onboarding of the developers. As you onboard to the developers of the project, they cannot touch the keyboard until they've demonstrated a sufficient level of domain proficiency and the area of expertise. You allow them to specialize as they desire, as needed. Also make improving domain knowledge part of the culture of the team. So have some kind of short weekly sessions that domain experts conduct. And the domain expert pose some kind of a question, and the developers have to respond by doing the research. Now, a good question is something that you cannot Google the answer for. It requires understanding the fundamentals of the business, of the industry. It's the things that add value the most. It's why this company even exists in the first place. What's the market differentiators? What are the trends in the industry? Why were things that were good as differentiators yesterday are not going to be good tomorrow? And you need to track the participation, track the interest, because if they're not participating, maybe you need to change how you're doing, or maybe give them a break and such. Here's a visualization of one such set of domain knowledge transfer in the energy project. And so this captures 15 weeks of domain knowledge exercises. And that document is then part of the onboarding of new developers, and they have to do the exercises themselves. Finally, definitely document extensively as you go. Documentation is more than just something that benefits posterity when it's somebody else's turn to maintain this system. It's a phenomenal way to communicate. And even to yourself, there's a saying that writing is God's way of showing you how little you understand. Even if nobody's going to read it beside yourself, merely trying to write it coherently, consistently, and concisely in a document shows you how little you understand, even to yourself. Certainly, if it's time to demonstrate to a domain expert or to the architect that you understand what this needs to do, you have to do it via communication. What are you going to do? You're going to draw on a whiteboard? No. Here's what this is supposed to do. Here's how it's going to do it. This is also a phenomenal way of onboarding something. If the level of complexity of the business is such that it takes 10 years to get a developer on board, you've failed. Developer need to read the relevant documentation, we're able to start adding value. Documentation is also how you validate your design. Who says it's a good design? Well, I need to tie the use case to the interaction diagram to the architecture. Documentation is a great way of doing a handover, because if developers cannot do the detailed design because they don't have the experience or don't have the domain knowledge, you have to document the detailed design and give it to them in the form of the document of the detailed design, the SDD. And they're not at liberty of changing anything at that point. You also develop the test cases against the documentation. You don't do it against the code.